Hello there, and welcome back to the Science Sleepy Minds, where tonight, with the lamp turned low and your pillow already warm, you're about to float up through the roof, through the clouds, through the thinning air, past the last blinking satellite, and out into the patient black deep of space, where the universe hangs around you like a slowly turning curtain of frost and fire. You're searching for something enormous tonight. You're searching for the largest planet ever discovered in the universe. And the funny thing is, nobody can quite agree on which one it is. You, a creature of a small blue world with mild weather and sensible gravity, are about to meet worlds so unreasonably huge that our familiar vocabulary, big, giant, massive, begins to crack at the edges and fall off like old paint. You probably wouldn't survive 5 seconds on any of them, not because of some dramatic monster or volcano, but because their atmospheres would crush you into a thin, confused film long before you had a chance to panic about the temperature. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And while you settle in, drop a comment telling me where you're listening from and what time it is for you, because I love picturing this sleepy little audience scattered across every time zone, all of us staring up at the same sky from different angles. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You begin with a simple question. The kind of question a child asks at the dinner table right before they are told to finish their vegetables. How big can a planet get? It seems like a perfectly fair thing to wonder. You know Jupiter is big. You've seen the pictures, the swirling bands, the red storm that has been churning for centuries, the moons lined up like patient school children. Jupiter is so massive it could swallow more than 1,300 Earths, and still have room for dessert. And yet, astronomers will tell you, with a little wince, that Jupiter is not really that impressive in the grand cosmic scheme. Jupiter is apparently a warm-up act. You drift deeper into the dark and the Milky Way stretches out around you like spilled powdered sugar on a black tablecloth. Somewhere in that sugar, spinning quietly around a star you will probably never visit, orbits a planet so large that calling it a planet feels almost rude. Out there are worlds wider than Jupiter, worlds heavier than Jupiter, and a small, argumentative group of worlds so in between that astronomers still can't decide whether they are planets, failed stars, or something entirely new. Historians, or rather planetary scientists, who are becoming the historians of our cosmic neighbourhood, still argue whether objects beyond 13 Jupiter masses should even be called planets at all, and it is the kind of argument that gets more heated the more coffee is involved at an astronomy conference. You sink further into your blanket because this is going to be a long, slow tour. Along the way you will meet bloated giants so fluffy they would float in a bathtub, if you could find a cosmic bathtub. You will meet a world that orbits its star backwards, as if it is pouting. You will meet a planet still being born, surrounded by a dusty cradle. You will meet a lonely super Jupiter, drifting so far from its host that it barely qualifies as family. And you will meet a few worlds so strange that even the astronomers who discover them can't quite agree on what they actually are. But before you can pick a champion, you need to understand a strange, embarrassing little secret of modern astronomy. Nobody entirely agrees on what a planet even is. You would think, after centuries of staring up at the sky, after mapping the solar system and demoting Pluto and sending robots to crawl across Mars, we would have nailed that definition down by now. But, like most things that involve committees, it got complicated, and the bigger the planets get, the messier the definition becomes. There's a mainstream, textbook version that says a planet is a roughly round body that orbits a star, doesn't fuse hydrogen, and has cleared its orbital neighbourhood. Fine. But once you start finding objects bigger than Jupiter, orbiting stars that are barely stars themselves, the whole tidy definition begins to squirm like a cat that doesn't want to be picked up. You smile a little at that, because you can already feel tonight's theme forming. Size, in space, is not a simple ruler. Size is a question. Size is an argument. Size is sometimes a philosophical mood. And tonight, while the fan hums, while your blanket settles around you, while the city outside goes about its unimportant business, you're going to drift through that argument, slowly, gently, until your eyelids decide the debate on their own. You don't have to remember any of it. You don't have to take notes. You don't even have to stay awake for the ending. The universe has been hiding these giants for a very long time, and it will keep on hiding them whether or not you manage to finish the video. You pull the blanket a little higher, because the next step of this journey takes you into definitions, and definitions, as you well know, are where a lot of bedtime stories go to quietly die. But stay with me, because this is the part that makes every other section make sense. Before you can crown the largest planet in the universe, you need to know what counts as a planet in the first place, and this is where astronomers suddenly become deeply, almost suspiciously, interested in their shoelaces. The story you probably remember from school goes like this. A planet is a big round thing that goes around a star. That was more or less the working definition for centuries, because frankly, it didn't need to be more complicated than that. You had the sun. You had 8 or 9 round things orbiting it, depending on whether you were taught before or after Pluto got voted off the cosmic island. Life was good. The solar system fit neatly on a classroom poster. Parents could quiz children with mnemonic devices involving pizzas and nachos. Nobody worried too much about edge cases. Then, in 2006, the International Astronomical Union got together in Prague and decided, in the way that adults sometimes do, that it was time to tighten the rules. A planet, they said, must do 3 things. It must orbit the sun. Well, any star, really. Although at the time they were mostly thinking about our own. It must be massive enough to have pulled itself into a roughly round shape under its own gravity. And it must have cleared the neighbourhood around its orbit, meaning it must be the gravitational bully of its lane, flinging away or absorbing most of the other debris. Pluto, bless its tiny icy heart, failed that 3rd test and was reclassified as a dwarf planet. And somewhere in an internet comment section, a war began that historians still argue whether it will ever truly end. Now, if you are paying very sleepy attention, you might notice that this definition has a kind of blind spot, the size of, well, a gas giant. It was designed to clean up our solar system's rulebook. It did not really grapple with the fact that we were, at that exact same time, discovering hundreds and then thousands of planets around other stars, planets that were nothing like the tidy little group we had at home. It didn't grapple with worlds drifting through interstellar space with no star at all, like cosmic orphans. It didn't grapple with objects barely smaller than the stars they orbited. The definition was a small, neat umbrella in the middle of a very strange storm. You drift a little, and that is fine, because I want you to picture a spectrum. On one end, you have tiny rocky worlds like Mercury, little more than a slightly oversized moon with ambitions. In the middle, you have worlds like Earth and Venus, the familiar Goldilocks siblings. Beyond them, you have the ice giants, Uranus and Neptune, which sound like they should be much colder than they actually feel in your imagination. Then come the gas giants, Jupiter and Saturn, those majestic striped monarchs. Beyond Jupiter, the spectrum keeps going. It keeps going a long way. You get worlds at 2 Jupiter masses, 5, 10, 12, 13, and somewhere around 13 Jupiter masses, a small but important thing starts happening inside the planet. Deep in its core, the pressure and temperature become so extreme that a specific kind of hydrogen, called deuterium, begins to fuse. Deuterium is a slightly chunkier cousin of regular hydrogen, and its fusion is much gentler than the fusion that lights up a proper star, but it is fusion nonetheless. That quiet little deuterium flickers the doorway. Above that threshold, many astronomers will stop calling the object a planet and start calling it a brown dwarf. A brown dwarf is a kind of almost star, the cosmic equivalent of a person who started writing a novel and never quite finished it. Too big to be a planet, too small to be a real star. It just glows faintly in the infrared and keeps its own counsel for billions of years. Remember this deuterium threshold, because we will keep bumping into it like a piece of furniture in the dark. But, and of course there is a but because this is space, not everyone agrees that mass is the right line to draw. Some astronomers argue that what really makes something a planet is not its mass, but how it was born. If it formed the way Jupiter did, by slowly gathering material in a disk around a young star, it is a planet, even if it is very, very large. If it formed the way a star does, by directly collapsing out of a cloud of gas, then it is a brown dwarf or a failed star, even if it ends up relatively small. In other words, one camp cares about the waistline, and the other camp cares about the family tree. And historians again still argue whether the field will ever settle on one neat answer. You might think this is academic hair-splitting, the kind of thing that only matters at faculty parties, but it matters for our quest tonight. Because when someone asks you innocently at a future dinner party what the largest planet in the universe is, the answer you give depends entirely on whose definition you're using. By radius, the answer is one thing. By mass, another. By formation history, yet another. And if you ask a grumpy astronomer at the end of a long day, the answer might be, honestly, we don't really know, and we're not sure we ever will. You feel the soft gravity of that uncertainty, and it is not as uncomfortable as you might expect. In fact, it is a little bit cozy, because this means the universe still has room for surprises. It means somewhere out there right now a planet far bigger than anything in our textbooks is orbiting a star whose light is still making its way toward us. A single photon, released thousands of years ago, whispering through the dark, carrying a little clue. One day, a telescope will catch that clue, and we'll rewrite the record books again. Remember that quiet little fact, because later tonight we will talk about just how close some of those telescopes already are to catching exactly those photons. You sink a little deeper into the pillow as we approach one of the fuzziest boundaries in all of astronomy, the boundary between a gas giant planet and a brown dwarf. This is a border region, and like all border regions, it is full of confused travellers, disputed territory, and more than one awkwardly dressed customs officer arguing about paperwork. You, tonight, are just drifting through it. Picture a perfectly ordinary gas giant, something Jupiter-like but scaled up. Jupiter itself is about 318 times the mass of Earth, which sounds like a lot until you realise Jupiter is still about 1,000 times less massive than our Sun. You can, in theory, keep stacking Jupiters on top of each other. 1 Jupiter, 2 Jupiters, 3 Jupiters, all the way up. For a while, as you add mass, the planet actually gets a little smaller, not bigger. That might sound backward, but it's because extra gravity squeezes the existing material tighter. More mass, more crush, same waistline, maybe even a thinner one. The planet doesn't really grow wider. It just grows denser, grumpier, and slightly squatter. This continues, believe it or not, until you reach about 13 Jupiter masses. Now 13 is not a cosmic magic number handed down from the universe. It is a threshold set by chemistry. Above about 13 Jupiter masses, the core of the object gets hot and squeezed enough to fuse deuterium. That deuterium fusion is a modest affair. It lasts only a brief cosmic moment, a few tens of millions of years, which for an object that will exist for tens of billions is barely a lunch break. But it happens, and many astronomers have decided that if an object can fuse anything at all, it has earned the brown dwarf stripe. You float a little closer and inspect a brown dwarf in your imagination. It is dim, dull red, about the size of Jupiter, surprisingly, because as you add more mass, the compression keeps the radius roughly the same. It is warm because of the leftover heat of its formation and the whispered glow of deuterium. It has weather. Yes, weather. There are clouds in brown dwarf atmospheres, and those clouds are not made of water or carbon dioxide. They are made of silicate dust, of molten iron droplets, of exotic salts. Imagine rainstorms of molten glass. Imagine drifting sand made of literal metal. Historians still argue whether the weather patterns on brown dwarfs count as climate in any meaningful sense, or whether they are too chaotic and too alien to fit that word. Either way, it is a lot to picture at bedtime. Try not to. Now push on further in mass. Above about 75 to 80 Jupiter masses, something more dramatic happens. The core gets hot and dense enough to fuse regular hydrogen, the way the sun does, and that is the real threshold of stardom. At that point, you've got a true red dwarf star, the most common kind of star in the galaxy. So somewhere between about 13 and 80 Jupiter masses, you have this transitional zone, the brown dwarf band, where the object is sort of a failed star and sort of a massively overachieving planet, and the whole community of astronomers kind of agrees that it is a bit of both and a bit of neither. Here's the quirky tidbit. Brown dwarfs were predicted before they were found. For decades, theorists said, look, there has to be a thing between Jupiter and the smallest stars, it's physically inevitable, and yet nobody could actually spot one. They are so dim in visible light that they essentially vanish into the darkness of space. It took until the mid-1990s, around the same time as the first confirmed exoplanets, for the first brown dwarf to be identified with confidence. It was named Tidy 1, after the volcano on the island of Tenerife, where the observations were made. The name has a kind of sleepy geological dignity to it. Tide. You can almost hear the syllables yawning. Now come the awkward questions, because out there in the real universe we find objects whose masses hover right around 13 Jupiter masses. Some clearly seem to have formed like planets, in a disk around a star, and then drifted or were slung into their current orbits. Others clearly seem to have formed like little stars, and inconveniently, some look like they could have formed either way. So what do you call them? If you're strict about mass, the cutoff is sharp, and anything above 13 is a brown dwarf. Period. If you're a formation history purist, you look at where the object came from and what it's doing, and if you're an exhausted observer at a telescope at 3 in the morning, you just call it an object and file the paperwork later. This matters tonight because our candidate planets for largest ever discovered tend to cluster right in this messy borderland. Many of them are 10, 12, 13, 14 Jupiter masses. Some are a little higher. Whether they count as planets depends on which definition you trust. So as we wander around meeting them, keep in mind that when someone says this is the largest planet ever found, what they often mean is this is the largest object that we are, for now, agreeing to call a planet based on our best guess at how it was born and how massive it is. It is a wonderfully humble claim dressed up in a dramatic headline. There's also a gentler reason the line is fuzzy. Even a brown dwarf and a planet of the same mass would look almost identical in a photograph. Same rough size, same rough colour, same lazy infrared glow when young. The difference is often in their history and in the spectrum of their light. Their atmospheres contain different chemical signatures, depending on whether they were heated by their own collapse, by nearby stellar radiation, or by the steady squeeze of internal pressure over eons. Spectroscopy is how astronomers peek at these signatures, and with squinted eyes and long spreadsheets, decide which label to apply. And here is one more small, quiet joke the universe plays. Some of the coolest brown dwarfs known are actually colder than some of the hottest planets. You could hold your hand near a very old, very dim brown dwarf and not burn it. You would be, essentially, warming your palm on a failed star. Meanwhile, certain hot Jupiters are so close to their host stars that their cloud tops could melt lead. So in a very real sense, planet and star are not about temperature. They are about history, mass, and the opinions of the person writing the caption under the telescope image. Keep that in your pocket as we slide onward. Now that your head is swimming in definitions, let's go back in time a little, because the story of how we even started finding planets around other stars is one of the most delightfully unlikely stories in modern science. For most of human history, the idea of other planets was pure speculation. People suspected they existed. Philosophers argued about them. Science fiction writers filled them with swamp cities and improbable empires. But nobody had ever actually seen one, or even detected one. As late as the 1980s, the honest answer to the question of whether other stars had planets was a polite shrug followed by, well, probably. You drift back to the late 20th century, when astronomers were beginning to suspect that something might be detectable. Stars, after all, are not perfectly still. If a planet orbits a star, the star wobbles very slightly in response, because both bodies orbit their shared centre of mass. Jupiter, for example, tugs the Sun around a point just outside the Sun's surface, which means our Sun is essentially doing a slow, cosmic hula. If you could measure that wobble from far away, you could infer a planet. The only problem is that this wobble is tiny. Jupiter moves the Sun by only about 12 meters per second, which is a walking pace. Earth moves the Sun by about 9 centimeters per second, which is slower than a snail on cough medicine. To detect those motions across tens of light years, you need absurdly precise instruments. Astronomers spent decades building and refining them, one careful screw at a time. The first confirmed detection of planets beyond our solar system came from a direction nobody really expected. In 1992, two astronomers, Alexander Wolszczan and Dale Frail, announced that they had found planets around a pulsar. A pulsar, you may remember, is the collapsed spinning corpse of a massive star, a kind of cosmic lighthouse flicking invisible beams across the galaxy. This particular pulsar, named PSR B1257+12, lay about 2,300 light-years away in the constellation Virgo. Its beams came through like clockwork, and by measuring the tiny irregularities in the arrival time of those pulses, Wolszczan and Frail realized that small bodies were tugging on the pulsar and changing the timing. They had found planets orbiting a dead star. And here's the quirky tidbit for tonight. The first confirmed exoplanets in history were not cozy little Earth twins orbiting a sunny yellow star. They were almost certainly scorched, radiation-blasted, possibly reborn worlds orbiting a stellar corpse. How they survived, or reformed after their star's death, is still debated. Historians still argue whether these pulsar planets were leftovers of the star's violent collapse or entirely new worlds built out of the debris afterward. Either way, in 1992, for the first time ever, humanity had solid proof that planets existed beyond our Sun, and they were already breaking our expectations on day one. But pulsar planets, as weird and wonderful as they were, did not really speak to the dream of finding planets like our own. For that, astronomers wanted to find a planet orbiting a normal star, a boring, stable, sun-like star. That took another 3 years, and it came with a bang. In October 1995, Michel Mayor and Didier Queloz, two astronomers at the University of Geneva, announced the discovery of a planet around the star 51 Pegasi, a sun-like star about 50 light-years from Earth. They found it using the wobble method, the radial velocity technique, with painstakingly calibrated spectrographs. The planet was named 51 Pegasi b, and for a long while it was simply known as the first exoplanet around a normal star. But 51 Peg b, as it came to be called, was immediately weird. It was at least half the mass of Jupiter, which was fine. It was a gas giant, which was fine. But it was orbiting its star at a distance of about 8 million kilometres, which is a tenth the distance from Mercury to the Sun, and it was whipping around its entire orbit in just 4 days. 4 days. A full year on 51 Peg b was shorter than a long weekend. This was not supposed to happen. According to the best planet formation theories of the time, big gas giants were supposed to form far from their stars, where it was cold enough for ice to stick together and grow into planetary cores. They were not supposed to live up against their star's face, sweating off their atmospheres. You can almost picture the scene. Somewhere in Geneva, Meyer and Queloz staring at their data, double-checking, triple-checking, asking each other whether this was real, and slowly realizing that yes, it was. The universe was already laughing at our assumptions. The first planet ever found around a normal star was the kind of planet textbooks had said could not exist. Astronomers quickly gave this kind of world a nickname: Hot Jupiter. A gas giant so close to its star that its upper atmosphere reaches thousands of degrees. Within a year of 51 Peg b, more hot Jupiters were found. Within a few years, dozens. A whole new class of planet had been uncovered, and none of them fit the old model. You shift in bed, because this is the kind of story that your brain wants to chew on softly as you drift. It is a reminder that science is not a tidy staircase. It is a series of startled discoveries. Every time we thought we had it figured out, the cosmos tapped us politely on the shoulder and showed us something new. Meyer and Queloz won the Nobel Prize in Physics in 2019, more than 2 decades after their discovery, sharing it with James Peebles for his cosmological work. By then, the field they had helped open had exploded. As of the mid-2020s, thousands of exoplanets have been confirmed, and thousands more candidates are awaiting follow-up. We now know that planets are not rare. Planets are the rule. Most stars in the galaxy have at least one planet, and many have several. We live in a galaxy that is absolutely stuffed with worlds, and we have only begun to survey them. Somewhere in that flood of discoveries are the largest planets we have ever found. They lurk in the lists, labelled with names that sound like computer passwords. WASP this, HATP that, HD something, TRES something else. Those letters and numbers hide worlds that would, if you could visit them, make Jupiter look like a slightly inflated beach ball. We're about to meet them, one by one, but first, in the next section, let's get a soft, sleepy handle on the detection methods that made it all possible. Because you cannot appreciate a record-breaking planet if you do not know how we managed to find it at all. Remember that cosmic hula the sun is doing? We'll keep coming back to that wobble. You let the idea of hot Jupiters roll around in your mind like a smooth, warm stone. Of all the surprises the early exoplanet era delivered, hot Jupiters were the most dramatic. They were big, they were close, they were hot. They were not supposed to be there. And they kept showing up everywhere astronomers looked because it turned out hot Jupiters were unusually easy to find. That combination of being large and close to their stars meant they produced some of the biggest wobbles and some of the clearest transit signals, which made them the first planets most surveys could confidently detect. It was a bit like searching for wildlife at night with a very weak flashlight and finding that every animal you caught in the beam happened to be an elephant. You know, statistically there must be smaller creatures too, but the elephants are the ones standing under your beam. Let's picture a classic hot Jupiter. Its star is a normal one, maybe a little bigger than the sun, maybe a little smaller. The planet orbits at a distance of just a few million kilometers, sometimes less, so close that if you could stand on its cloud tops and look up, the star would hang above you like a monstrous boiling hearth, filling nearly half the sky. The planet's day side would be permanently roasted at thousands of degrees. The night side would still be hot, but less blistering, because the planet is usually tidally locked, meaning it shows the same face to its star forever, the way the moon shows the same face to Earth. This tidal locking leads to some deliciously strange meteorology. On a tidally locked hot Jupiter, the day side never cools, and the night side never warms, at least not by direct starlight. The only way heat gets redistributed is through screaming supersonic winds that tear around the equator at speeds that make Earth's jet streams look like a gentle breeze in a park. These winds can blow at thousands of kilometers per hour, dragging superheated gas from the day side to the night side and back again. And on the Terminator, the line between day and night, you get truly alien weather. On some hot Jupiters, the night side may be cool enough for strange clouds of vaporized iron or molten silicate to condense, meaning, yes, you could have rain made of metal. Historians still argue whether the term rain even applies to droplets of molten titanium oxide falling sideways at hurricane speed, but semantically, it fits. Here's the mainstream fact to keep tucked in your sleepy little pocket. Hot Jupiters, despite how common they seem, probably represent only about 1% of all planets in the galaxy. We find them easily, but they are actually pretty rare. Most stars do not have a hot Jupiter. Most stars have smaller planets in calmer orbits. The hot Jupiters are the loud kids in the cosmic classroom, not the majority. Now for the quirky fringe tidbit. Some hot Jupiters are being actively eaten by their stars, not quickly, not in a single gulp. But over millions of years their atmospheres are being boiled off and their orbits are slowly spiraling inward, and eventually they will be dragged into the star itself. Astronomers have already caught a few in this state of slow-motion consumption. One such planet, HD 189733b, has a comet-like tail of gas streaming off of it as its atmosphere is blown away by stellar radiation. It is a planet with a tail which sounds like something out of a children's book, but is absolutely real. Some hot Jupiters look, at a great distance and in the right wavelength, rather like giant cosmic tadpoles, trailing their own atmospheres behind them as they flee. Okay, light joke. If you were a real estate agent in the galaxy, hot Jupiters would be the worst listings. You simply could not sell them. Imagine the brochure. Beautiful views of your local star, up close, very close, somehow even closer. Stunning year-round sauna climate. Eternal daylight on one side of the house, dramatic backlit moods on the other. Wind speeds perfect for taking off the roof. No water, no solid ground. Skies full of melted glass. Low gravity on the outer atmosphere. Absolutely crushing gravity a few miles down. Pets not recommended. Plants not possible. Pets now cremated. Congratulations on your new home. But hot Jupiters are not just a weird curiosity. They're essential to our story about the largest planets, because hot Jupiters include some of the puffiest, widest planets ever found. Remember that a planet does not gain girth the more mass you add. Past a certain point, more mass means more squeeze, not more size. What does make a planet fatter, however, is heat. The hotter a gas giant is inside, the more its atmosphere swells outward, like a balloon held over a radiator. Hot Jupiters, bathing in an intense stellar radiation, and often with bizarre internal heating from tides and magnetic fields, sometimes end up puffed out to sizes far beyond what mass alone can explain. So when we ask which planet is the widest ever found, measured purely by radius, we tend to end up in the hot Jupiter aisle of the planetary supermarket, and there, we meet a few absolutely ridiculous examples. Worlds with radii more than 1.5, even nearly 2 times Jupiter's radius, while weighing only a fraction of Jupiter's mass. Worlds with densities so low that if you could somehow drop them into a cosmic bathtub big enough, they would float. Worlds that astronomers half-jokingly call cotton candy planets, because that is genuinely what their density profile resembles. This is where the real fun of our quest begins. The search for the largest planet in the universe, at least by radius, is basically the search for the most ridiculously bloated hot Jupiter that can still hold itself together gravitationally. Too puffy, and its atmosphere starts streaming off into space. Too cold, and it won't inflate. It's a Goldilocks problem, and Goldilocks, as usual, is picky. Before we go meet specific names, TRES 4b, WASP 17b, HATP 67b, let's quickly pause on the methods by which we can even measure a planet's radius from across the galaxy. Because you might be wondering, sensibly, how anyone knows how wide a planet is when we can't see it at all. Most planets are never imaged directly. We only know they exist because of their subtle effects on their star's light. Mass and radius are separate things, measured by separate techniques, and it is the careful combination of those techniques that lets us say, with any confidence, how fluffy or how dense a world far away really is. That's what the next section is for, and after that we'll dive into the champions. Remember that cosmic hula, the wobble, the tadpole tail and the metal rain, because each of these will come back as we stack up the candidates for the largest planet ever discovered. You settle in, warm and still, as we take a slow, dreamy tour of the actual detective work behind planet finding. This is the quiet, patient, deeply nerdy engine behind every big headline. Without these methods, we would have no idea any of these enormous planets exist, and the methods themselves are, at their heart, just clever tricks of light and gravity, dressed up in expensive equipment. Method number 1 is the wobble method, properly known as the radial velocity technique. You remember the cosmic hula from earlier, the fact that a star is not perfectly fixed in space, but orbits the common centre of mass it shares with its planets. When the star wobbles toward us, its light is compressed into slightly bluer wavelengths. When it wobbles away, its light stretches into slightly redder wavelengths. This is the famous Doppler effect, the same reason an ambulance siren drops in pitch as it passes you on the street. Astronomers use spectrographs to split a star's light into a fine rainbow, and they watch where the dark absorption lines in that rainbow are. If those lines slide ever so slightly back and forth over days, weeks, or years, a planet is probably the cause. The amount of sliding tells you the planet's minimum mass. The time it takes to slide and return tells you the orbital period. The method is beautiful, but it has a weakness. It mostly tells you the minimum mass, not the exact mass, because you don't know the tilt of the orbit relative to Earth, and it does not tell you the planet's radius at all. You can have a very massive planet and a very fluffy planet producing the same wobble. The technique cannot tell them apart. Method number 2 is the transit method. This one is easy to picture. Imagine a star as a distant lamp. A planet orbiting it will, if its orbit is tilted just right, occasionally pass directly between the lamp and us. During that passage, it blocks a tiny fraction of the lamp's light. The star appears to dim very slightly, like a moth flying briefly in front of a porch light. Modern space telescopes can measure dips in brightness of less than 1 part in 10,000, which is what lets us spot planets far smaller than their stars. The deeper the dip, the wider the planet. So, and this is the crucial bit for tonight's quest, the transit method is the technique that tells you a planet's radius. Combine a transit with a radial velocity measurement, and you now know both the mass and the radius. Divide mass by volume, and you get density. Density is where the cotton candy planets reveal themselves. Light joke. The transit method essentially means we find other worlds by watching for the faintest possible flicker in the brightness of a star, like a security guard becoming convinced someone is in the warehouse because the overhead light dimmed by 1/1,000,000%. It is the most patient kind of surveillance. NASA's Kepler mission took this surveillance to its purest form, staring at a single patch of sky in the constellations Cygnus and Lyra for years, watching about 150,000 stars for dips. By the end, Kepler had found thousands of planets, many of them small and rocky, many of them just weird, and it completely transformed our picture of the galaxy. Method number 3 is gravitational microlensing. This one is the most cosmic. According to Einstein's general relativity, massive objects bend light. If a distant star happens to pass almost exactly in front of a more distant background star, from our perspective, the foreground star's gravity acts like a lens, briefly magnifying the background star's light. If the foreground star has a planet, that planet adds an extra little bump to the light curve. Microlensing can detect planets at great distances, and even planets with no host star at all, floating freely through interstellar space. It is, however, a one-shot method. The alignment that makes the detection possible never happens again. You cannot go back and observe the planet a second time. You get a single cosmic photograph, and then the lens moves on. Historians still argue whether some microlensing detections represent true free-floating planets, or simply planets on very wide, hard-to-confirm orbits, and the debate is an active one. Method number 4, the most intuitive but the hardest, is direct imaging. This just means taking a picture of the planet. The problem is that a star is usually billions of times brighter than any planet around it, so the planet is drowned in starlight like a firefly next to a stadium spotlight. To take a real picture, astronomers use devices called coronagraphs, which are essentially carefully shaped masks that block out the star's direct light while letting the planet's much fainter light reach the detector. Direct imaging works best for planets that are very far from their stars and very young, because young planets are still glowing with the heat of their formation. This method has given us the most dramatic images in exoplanet science, including some of the large superjupiters we'll meet later, like ROXs 42Bb and HD 100,546b. Direct imaging is where you actually get to see another world, as a tiny, lonely dot of light next to a blacked-out star. Genuinely spooky. Method number 5 is astrometry, which is a fancy word for measuring the precise position of a star over time. If a planet is present, the star's position will trace out a tiny looping path as it orbits the common centre of mass. It is basically the wobble method done sideways, tracked by position instead of by light shift. The European Space Agency's Gaia mission has been doing exactly this for billions of stars for over a decade, and in the coming years its astrometric data is expected to reveal many planets that other methods missed, especially the big far-orbiting ones that we'd love to add to our largest planets list. You start to see a pattern. Each method has its blind spots and its strengths. The wobble method loves big planets close in. The transit method also loves big planets close in, but only if their orbits are tilted just right. Microlensing loves everything, but only once. Direct imaging loves big, young, far-out planets. Astrometry loves big planets on long orbits. There is no single method that finds every type of planet. To build a real catalogue, you stack them together like overlapping sheets of imperfect glass that together let you see the whole scene. And tonight's candidates for the largest planet ever discovered, the bloated hot Jupiters, the super Jupiters in wide orbits, the borderline brown dwarfs, have been found by different combinations of these methods. Some have transits, some have direct images, some have wobble and transit both. Which method found them affects what we know about them and how confident we are. TRES-4b, for example, was found by transits, so we know its radius extremely well. ROXs-42bb was directly imaged, so we've literally seen its light. HD 100,546b is a direct imaging candidate, which means its status is still being argued. Remember this lineup as we head into the next section and finally meet a planet that looks, by the numbers, like a blue whale trying to masquerade as a water balloon. TRES-4b. Say it softly because honestly it sounds like a printer driver. And yet, for a good while after its discovery in 2007, TRES-4b was the largest exoplanet known by radius. It came out of a survey called the Transatlantic Exoplanet Survey, a small network of ground-based telescopes that patiently watch stars for the faint wink of a transit. TRES-4b was their fourth confirmed catch, hence the 4, and B is standard astronomical shorthand meaning roughly the first planet found around this star, with a being reserved for the star itself. TRES-4b orbits a star called GSC 02620-00648, which is a name almost nobody uses at parties, about 1,400 light-years from Earth in the constellation Hercules. The star is a little bigger and hotter than our Sun, a bit further along in its stellar life, and around it, in a tight orbit that takes just 3.5 days, whizzes this strange, enormous puffball. The planet's radius is about 1.7 times the radius of Jupiter, which does not sound very dramatic until you do the math on volume. Volume scales as the cube of radius, so 1.7 cubed is roughly 4.9. TRES-4b has nearly 5 times the volume of Jupiter. 5 Jupiters could fit inside it with room left over for some cosmic clutter. Now, the twist. TRES-4b is less massive than Jupiter. It weighs about 0.9 times Jupiter's mass, maybe a little less depending on the estimate. So imagine taking all of Jupiter, shaving off a bit of mass, and then bloating it up to almost 5 times its current volume. The density that results is something like 200 kilograms per cubic meter, which, to put in everyday terms, is less than the density of cork, less than a pine plank, less than a block of balsa wood, less than, I'm not exaggerating, whipped cream. TRES-4b is, by density, comfortably puffier than most of the dessert aisle of your local supermarket. If you could find a swimming pool big enough to hold it, and if the planet did not instantly devour the pool and the Earth, and probably your entire solar system, it would float. This raised, at the time, an immediate and slightly embarrassing question among astronomers. How on Earth, or off it, is this planet so large? Based on standard models of gas giant physics, a planet with TRES-4b's mass and age should be significantly smaller. Something was inflating it. Something was keeping its interior hot enough to puff its atmosphere outward against its own gravity. And whatever that something was, it seemed to be operating in a number of other hot Jupiters too, because TRES-4b was far from alone. Astronomers had already been noticing that many hot Jupiters were systematically larger than their models predicted. TRES-4b was an extreme headline-grabbing member of a growing club. You lean into the sleepy absurdity of it for a moment. A planet made almost entirely of hydrogen and helium, the 2 lightest elements in the periodic table, puffed up around roughly the mass of Jupiter, orbiting a bigger, older star whose radiation is relentlessly hammering its day side. The planet's temperature is probably around 1,700 Kelvin, which is about 1,400 degrees Celsius or 2,600 degrees Fahrenheit. Hot enough to melt steel easily. Hot enough that on its day side you'd have no clouds of water, not even close. You'd have silicate clouds clouds made of vaporized rock. Imagine fog rolling in and realizing the fog is powdered granite. Light joke for tonight. TRES 4b is essentially the universe's least aerodynamic gas giant. Jupiter is packed and sturdy, a kind of cosmic linebacker. TRES 4b is the soft cousin who shows up to family reunions in a fluffy robe and tells everyone to just take a moment and breathe. Gravitationally, it is actually in some trouble, because its low density and high temperature mean its upper atmosphere is only loosely held on. Hot Jupiters like TRES 4b often have extended comet-like upper atmospheres, being slowly but steadily stripped away by stellar radiation. So, yes, TRES 4b is probably losing itself to space, a few molecules at a time, for as long as its star keeps shining. The mainstream historical fact here is that TRES 4b, when announced in 2007, beat the previous record holder, HATP1b, to become the largest known exoplanet by radius. It held that informal title for only a little while, as new discoveries rolled in because the late 2000s and 2010s were a gold rush of puffy planets. WASP this, Kepler that. Each month brought another candidate. The largest crown kept changing heads so quickly that astronomy news sites basically stopped announcing it with the word record-breaking and started using it more like a passing comment. The quirky tidbit is that TRES 4b was discovered using a rather humble setup. The TRIS survey used small 10cm telescopes. 10 centimeters. That's basically the size of a decent amateur rig. Compared to the giant multi-ton instruments on mountaintops, the TRIS telescopes were practically toys. And yet, because they stared at thousands of stars over long periods and could detect the 1% dip caused by a Jupiter-sized planet transiting its host, they made real, respected discoveries. It is a reminder that in astronomy, patience and clever software can sometimes beat raw aperture. Historians, well, astronomers, still argue whether the inflation mechanism for planets like TRES 4b is dominated by tidal heating, ohmic dissipation from induced electrical currents, or simply by the relentless deposit of stellar energy into the deep atmosphere in ways that slow its cooling. Different models fit different planets better. TRES 4b, with its extreme puffiness, is often cited as a key test case for these theories. Every new observation, every better measurement of its transit shape or atmospheric spectrum is fuel for the ongoing argument. You, softly horizontal, can appreciate this as a cosmic metaphor. We find an object, we measure it, we think we understand it, and then the measurements keep refining and refining, and suddenly our understanding needs to grow to fit. In a way, TRES 4b taught us that our models of gas giants had a serious hole in them. Jupiter, which we thought of as the archetype of a gas giant, is apparently a cool, compact outlier in the broader galactic catalogue of gas giants. Most big planets out there, if the samples we found are any guide, are hotter, weirder, closer to their stars, and more bloated than Jupiter. Jupiter is the neat one. TRES 4b is the chaos. Before we leave TRES 4b and move on to the next bloated wonder, just sit for a moment with the mental image. A planet bigger than Jupiter, almost the volume of 5 Jupiters, orbiting a star close enough that it completes a full year every 3.5 days. Atmosphere slowly boiling off into space, winds tearing across its day side, night side glowing faintly in the infrared. And if you could reach out and push it gently, a tiny cosmic hand against a cotton candy giant, you would feel, very strongly, that the universe has a sense of humour. Remember this puffball, because when we meet HATP67b shortly, you'll see it has TRES 4b beat. Now drift with me over to a different stretch of the galactic neighbourhood, because WASP-17b is a planet that does not just sit around being puffy. WASP-17b is a planet with attitude. It is big, it is hot, and it is frankly going the wrong way. Think of it as the cosmic equivalent of a driver cheerfully heading the wrong way down a highway, while the rest of the traffic honks in astonished outrage. WASP-17b was discovered in 2009 by the Wide-Angle Search for Planets, or WASP, a collaboration of telescopes in the Canary Islands and South Africa. Their job was, once again, transit hunting. Their survey produced a long list of useful discoveries, but WASP-17b stood out for two reasons. First, it was gigantic. At about 1.9 to 2 times Jupiter's radius by some early measurements, it was at the time one of the largest known planets. Second, its orbit was retrograde. Retrograde means the planet is orbiting its star in the opposite direction from the star's rotation. And this matters a lot because in the standard theory of planet formation, a planet is born out of the same flattened disk of gas and dust that gave birth to its star. If you are born from that disk, you inherit its direction of spin. You should orbit the way your star spins. All the planets in our solar system, for instance, orbit the Sun in the same direction the Sun rotates. It is the cosmic equivalent of being born into a family that marches in step. The fact that WASP-17b is marching in the opposite direction means something in its life story went dramatically sideways. Astronomers immediately asked, how did WASP-17b get into a retrograde orbit? The leading guesses involve violence, which is honestly so often the case in astronomy. Maybe WASP-17b started out far from its star, as gas giants usually do, and then gravitational interactions with another massive planet or a passing star flung it onto a wildly tilted, even flipped orbit. Maybe the host star's disk was itself tilted relative to the star. Maybe the system was part of a binary, and a passing companion's gravity twisted the whole setup. Historians still argue which of these mechanisms dominates, and it is likely a mix. Here is the quirky tidbit. WASP-17b, with its combination of huge radius, moderate mass, and retrograde orbit, was probably the first world of its kind clearly identified, but it was not the last. After its discovery, astronomers began noticing that quite a few hot Jupiters have surprisingly tilted or even fully reversed orbits. This class of planets has become a quiet laboratory for studying how planetary systems evolve after they form. The cozy, tidy picture of the solar system, where everyone lines up neatly, is, it turns out, not universal. Plenty of systems are messy, and WASP-17b was one of the first to tell us so out loud. Light joke. WASP-17b is essentially the galaxy's most passive-aggressive planet. It is a huge, warm, soft gas giant, and it spends its entire existence orbiting backwards, as if to say, I heard you about how planets are supposed to behave, and I considered your opinion, and here is my considered response. It probably has winds in its atmosphere too, and those winds naturally go the other way from the winds on comparable prograde hot Jupiters, which means WASP-17b is simply a contrarian on every available scale. Physically, WASP-17b orbits a star called WASP-17, a bright yellow-white main-sequence star about 1,300 light-years from Earth in the constellation Scorpius. The planet is in a roughly 3-day orbit, extremely close to its star, and its temperature is around 1,500 to 1,700 Kelvin. Its mass is about half Jupiter's mass, but its radius is nearly twice Jupiter's, which gives it an even lower average density than TRES 4b by some calculations. Some measurements put it under 50 kilograms per cubic meter, which is lower than styrofoam. Yes, styrofoam. Think about this for a second. There exists, in our galaxy, a planet whose average density is less than the foam used to ship breakable ceramics. It is a packing peanut planet with a retrograde chip on its shoulder. Being so puffy and so close to its star, WASP-17b is also slowly losing its atmosphere to space. Stellar radiation heats the upper layers until they escape the planet's relatively weak grip and stream off into the void. This is a common fate for puffy hot Jupiters, and it is another reason these giants, while enormous right now, will probably not be quite so enormous a few 100 million years from now. Planets like WASP-17b are, in a sense, in their golden bloated middle age, before the long, slow contraction of age and stellar radiation whittles them down. But even besides its size and its backwards tantrum, WASP-17b had another trick up its sleeve. In 2023 and subsequent years, observations from the James Webb Space Telescope, that marvellous infrared space observatory, probed WASP-17b's atmosphere with exquisite precision. They found evidence of quartz nanocrystals, tiny sand grain-like particles of silicon dioxide, suspended in its upper clouds. Yes, WASP-17b, on top of being a backwards puffball, appears to have clouds made of microscopic glass. Imagine that for a moment. Clouds of glass like crushed rock candy, drifting through a sky so hot that lead is a gas. You can almost hear the tiny tinkling if you imagine hard enough, though of course in space, no one would hear anything. The mainstream historical fact to remember tonight is simply that WASP-17b confirmed, with dramatic flair, that many exoplanetary systems are not as orderly as ours. The discovery of a retrograde gas giant meant that theorists could no longer assume that planetary orbits mostly line up with their stars' spins. Planet-star alignment became a thing you had to measure for each system, and once astronomers started measuring, they found all sorts of misalignments, some modest, some wild. The fringe tidbit, or at least the deliciously speculative one, is that some researchers have wondered whether WASP-17b might have had companions once, planets now ejected into interstellar space or scattered into the star itself as part of whatever gravitational tango flipped its orbit. If so, then somewhere in the dark between the stars there may be former siblings of WASP-17b drifting alone. These would be rogue planets, a class we will briefly visit when we talk about direct image giants in later sections. You rest with that picture for a moment. A massive, puffy gas giant wider than almost any we've ever found, wheeling the wrong way around a perfectly normal yellow-white star. Quartz clouds shimmering in its upper atmosphere. A thin trail of escaping hydrogen fluttering behind like a long sigh. And all of this, 1,300 light-years away, is happening right now, has always been happening in the lifetimes of everyone you've ever known, utterly indifferent to our telescopes and our headlines and our arguments about what counts as large. Remember WASP-17b, because its combination of wide radius and dramatic history makes it a frequent candidate when people argue about the biggest planet title. Even if, as we will now see, there are wider worlds still. HATP-67b, another cosmic password of a name. HATP stands for the Hungarian Automated Telescope Network Planet Survey, a set of small automated telescopes that, like the Trizon WASP surveys, have been quietly churning out planets by watching for transits over many years. The 67 simply means this is the 67th confirmed planet system from the survey, and B, as always, is the planet. HATP-67b is a strong candidate, depending on your preferred measurement, for one of the largest confirmed exoplanets by radius ever found. You drift toward it. HAT-P-67b orbits a star roughly in the constellation Hercules, about 1,200 light-years away, give or take. Its host star is not quite like our Sun. It is what astronomers call a subgiant, a star that has used up the hydrogen in its core and is beginning the slow, grand expansion toward red giant status. It is fatter, hotter, and more luminous than the Sun. Living near a subgiant is, from a planet's point of view, not a peaceful retirement community. It is, to extend the retirement metaphor, more like a retirement community gradually catching fire. HATP 67b is enormous. Its radius, in various measurements, comes in at about 2 times Jupiter's radius, which, if you remember, the volume calculation from TREES 4b means this planet has roughly 8 times the volume of Jupiter. 8 Jupiters could, in principle, fit inside it, and yet its mass is believed to be less than half of Jupiter's, maybe around 0.34 Jupiter masses in some estimates. Its density is therefore absurdly low, comparable to, again, some kinds of foam. If you insisted on the cotton candy planet label, HATP 67b is a strong champion. Now here is the kicker. HATP 67b is being cooked from both sides. It is close enough to its subgiant star to be intensely irradiated. Its equilibrium temperature is somewhere around 1900 to 2100 Kelvin, blisteringly hot, and its host star is itself expanding. Over cosmic time, the star will grow larger, hotter, and more luminous. The planet will be baked ever more intensely. Its atmosphere is already losing mass to space, streaming off in a long, faint tail. HATP 67b is, in a sense, a planet being slowly exhaled by its star. Historians, by which I mean planetary scientists, still argue whether HATP 67b is in the process of becoming fully unbound from its star, in which case we are watching a gas giant effectively be eaten in slow motion. The rate at which its atmosphere is escaping, and the fraction of the planet that will remain in, say, 1 billion years, depends on exactly how much the host star expands and how tightly the planet's gravity can keep its outer layers in place. You get a sense from a quick review of the literature that this is one of those planets that new graduate students are gently assigned because there is a lot of material to study and a lot of honest uncertainty still. The light joke tonight is that HATP 67b is the galaxy's most patient suicide note. It is not in a hurry. It is simply slowly, gently, over millions of years, offering its outermost layers up to the void, writing a novel-length farewell in hydrogen and helium. The star reads a little of it every day, politely, and then goes on shining. Physically, if you could somehow stand in the upper cloud deck of HATP 67b, you would find the star taking up an enormous portion of the sky, glowing blue-white, beating down with brutal force. Radiation would tear at the uppermost atmosphere. Silicate clouds, perhaps, or even more exotic condensates might shimmer at lower levels, and the atmosphere would simply be enormous. A gas giant that is twice Jupiter's radius is twice as wide. You could fall through its cloud layers for a very long time before anything resembling a solid core even began to pretend to exist, and the pressures you would encounter along the way would crush any known spacecraft material into a tidy puddle of denser stuff. The quirky fringe tidbit is that the category HAT-P-67b belongs to, the ultra-low density hot Jupiters, has been used by theorists as a playground for models of planetary inflation. Some think the unusual combination of a puffy planet and an evolving subgiant star is not a coincidence. As the star expands and increases in brightness, it may dump extra energy into the planet's atmosphere, which inflates it further, which makes it easier to lose mass, which then changes the dynamics again. The planet and the star are in a kind of slow, strange feedback loop, and nobody is entirely sure how it ends. There's also a lovely mainstream fact here. Because HATP 67b is so large and orbits such a bright star, it has become a favourite target for atmospheric studies using the James Webb Space Telescope and ground-based spectrographs. Its large size makes its transit signal very deep, which means the dip in starlight as it passes in front of its star is easy to see, and during that dip, a tiny fraction of the starlight filters through the planet's upper atmosphere. That filtered light carries chemical fingerprints. Astronomers can, with care, read those fingerprints and say, there is water here, there is carbon monoxide here, there are traces of this or that molecule here. Over time, HATP67b has become a sort of test bed for learning how to read the atmospheres of giant, puffy, strange worlds. Okay, another light joke. HAT-P-67b is basically the fluffiest, most overstyled pillow in the Cosmic Hotel, and its star is the hotel's radiator, stuck on max in the corner of the room. Anyone coming into that room is going to notice immediately that the pillow is absolutely enormous and also very, very warm and gently evaporating around the edges. You would not want to sleep on this pillow, but from across the galaxy you can admire its vibe. HATP67b has, at various points, been listed as the largest confirmed exoplanet by radius, depending on how one weighs competing measurements from other candidates, like WASP-17b, WASP-12b, KELT-9b, and other extreme hot Jupiters. The truth is that largest by radius is a title that keeps sliding around, because each year someone remeasures a candidate with better instruments, and the rankings shuffle. But HATP67b is consistently near the very top. Even if it is eventually demoted to second or third, it will remain a world of spectacular puffiness, a textbook example of what happens when you combine a low-density hot Jupiter with an aging expanding star. You soften into that image. A planet 2 Jupiters wide, barely a third of Jupiter's mass, orbiting an increasingly furious subgiant whose own death spiral is just beginning. Atmospheric atoms rising off its dayside like sighs, a long, thin, faintly glowing tail behind it, a cool, dark far side where, perhaps, clouds of something exotic condense under low gravity. And out beyond all that, space, black and patient, waiting for the rest of the planet to finally, politely, give up. Remember HATP67b because it anchors our short list of biggest planets by radius. And in the next section, we will pivot to a very different kind of monster. Worlds that are not especially wide, but absolutely ferocious in mass. Now we zoom out, literally, because the next kind of largest you're going to meet lies far, far from its star. It is called ROXs 42bb. It orbits a young, cool star in a star-forming region called Ophiuchus, about 460 light-years from Earth. It is, as far as anyone can tell, about 9 Jupiter masses, and it orbits its host star at a distance of roughly 150 astronomical units, where 1 astronomical unit is the distance from Earth to the Sun, 150 times that. That is well beyond the orbit of Pluto if you scaled it to our own system. Remember, the planet is 9 Jupiter masses. Remember, it is so far from its star that if you put it at that distance around our Sun, it would be 3 or 4 times further out than Pluto's average orbit. Remember, it was discovered not by the wobble method, not by transits, but by direct imaging. Astronomers literally took pictures of it. 2 separate dots of light in the same field of view, a faint young star and a fainter, warm giant glowing nearby, clearly gravitationally associated with it. ROXs 42bb is one of those incredible cases where, yes, you're looking at another world. Now, the obvious sleepy question: how on earth did a planet that big end up so far from its star? In our own solar system, Jupiter, which is much less massive, lives around 5 astronomical units from the Sun. Neptune, which is less massive still, hangs out around 30. ROXs 42bb is several times further than Neptune, and it's 9 Jupiters heavy. The standard core accretion theory, the classic picture of planet formation, really struggles here. In that theory, planets grow slowly from colliding dust and pebbles, forming rocky cores, and then, once a core is big enough, it gravitationally hoovers up gas to become a gas giant. The trouble is, at 150 astronomical units, everything is so spread out and so cold and so sluggish that you cannot realistically grow a 9 Jupiter mass planet within the lifetime of a protoplanetary disk. The physics simply does not want to cooperate. So how did ROXs 42Bb happen? There are a few possibilities. It might have formed closer in and then been gravitationally kicked outward by another massive planet during the chaotic early years of the system. Or it might have formed directly from gravitational instability in the outer disk, where a patch of gas and dust became dense enough to collapse directly into a planet, rather than building up pebble by pebble. Or, and this is where it gets philosophically interesting, ROXs 42b might have formed more the way a small star does, by collapsing out of a cloud, and then ended up bound to this star as a companion. In that case, it's less a planet and more a very low-mass companion. Historians, planetary scientists, still argue which model best fits ROXs 42Bb, and the answer probably shapes how we categorize a lot of other super Jupiter candidates too. Here's the quirky tidbit. ROX 42. BB orbits very slowly. At that distance, a single orbit around its host star takes thousands of years. Thousands! The entire lifespan of human civilization, from the earliest cities to today, represents only a small fraction of 1 year on ROXs 42Bb. If you were floating in its upper atmosphere, you would never feel any sense of progression around your star. The star would hang, essentially fixed in the deep black sky, a tiny reddish-orange bead, far smaller than our sun appears from Earth. Its light would be dim, its warmth negligible. The planet's own internal heat, left over from its formation, would matter more to its temperature than the distant star. Light joke for tonight, ROXs 42Bb is the galactic equivalent of that one cousin who lives so far out in the countryside that Google Maps gives up halfway there. Technically related to the family star, yes. Actually invited to Thanksgiving, not really. Will they make it by Christmas? Unclear. But their Christmas card finally arriving will be quite nice, though slightly dusty. Because the planet is young, the system is only a few million years old, a cosmic infant. ROXs 42. BB is still glowing strongly in the infrared with the heat of its formation. That is why we can see it at all. As planets age, they cool down, and their own light becomes much fainter compared to their stars. Young planets are the best targets for direct imaging for precisely this reason. ROX 42Bb is, essentially, still radiating baby fat. Its temperature is estimated at around 1800 to 2000 Kelvin, comparable to the surface of a dim, cool brown dwarf, and we can peek at its spectrum and see the faint fingerprints of its atmosphere. What is in that atmosphere? Mostly hydrogen and helium, as with all gas giants, but astronomers have found hints of carbon monoxide, water vapour and exotic condensates. Whether dust clouds float through its skies, whether it has internal weather patterns similar to Jupiter's, whether it has anything like a ring system, all of these remain open questions. We simply do not have the resolution to resolve its surface features yet. What we have is a tiny dot of warm infrared light, and even that is extraordinary. The mainstream historical fact tonight is that ROXs 42Bb was one of several directly imaged companions in the early 2010s that forced the planet formation community to seriously reckon with super Jupiters on wide orbits. Others in this loose club include HR 8799b, C, D and E, the first planetary system ever directly imaged, Fomalhaut b, whose status has been debated and redebated, 2M1207b, which we will meet shortly, and HD 106906b, which lives at an even more absurd distance from its star. Each of these discoveries was a small earthquake in the field. Together they pushed us to imagine a galaxy in which wide-orbit super-Jupiter-class planets are not a rare exception, but a regular feature, possibly formed by mechanisms we're only beginning to understand. If, for our quest tonight, we define the largest planet ever discovered in terms of mass, up to, but not past, the brown dwarf threshold, then ROX 42BB is a solid candidate, even if not the heaviest. Some directly imaged companions come in at 12, 13, even 14 Jupiter masses, right at the fuzzy edge of the planet vs brown dwarf line. In that region, the word largest becomes a lawyer's game. RX S42. BB had about 9 Jupiter masses, sits comfortably on the planet side of most definitions, but its cousins wander closer and closer to the border, making rankings genuinely difficult. You linger in the quiet of its orbit, the stillness of a world that takes millennia to circle its own star. Think of the slow eternity out there, a warm, dim giant turning very gently in a vast cold garden of space, its year measured in human lifetimes, its glow a faint rust-coloured whisper in a crowd of much brighter stars. The photons from its atmosphere, which reached your telescope tonight, left the planet around the time of the Viking Age here on Earth. They have been travelling patiently ever since. Remember that, and remember ROXs 42BB, because in the next section we're heading toward an even stranger giant, a young world whose very nature is still up for grabs. GQ Lupi b, another delightfully clinical name hiding a strange, lovely mystery. GQ Lupi is a young star in the constellation Lupus, the Wolf, about 450 light-years from Earth. It is a T-Tauri star, which is the astronomical term for a very young, active star still in the process of settling down into its main sequence life. Around this youthful, cranky star, in 2004, astronomers using the Very Large Telescope in Chile directly imaged a faint warm companion. They called it GQ Lupi b, and ever since the question of what GQ Lupi b actually is has floated, unresolved, like a thought you can't quite grab before sleep. Here is the trouble. GQ Lupi b is estimated to be somewhere between about 1 and 40 Jupiter masses. That's not a small range. That's a range that spans giant planet, borderline planet / brown dwarf, and solid brown dwarf, all in one uncertainty bar. The reason the uncertainty is so large is that, for a directly imaged young companion, we have to infer its mass from models that translate its observed brightness and temperature into a mass given its age. Those models, especially for very young objects, have huge uncertainties. Is the planet a few million years old, glowing furiously with leftover formation heat? Or is it a little older, glowing less, and therefore needing more mass to match the observed brightness? The difference between those answers is enormous. GQ Lupi b orbits at a wide distance, roughly 100 units from its star, similar in scale to ROXs 42BB. Like ROXs 42BB, it is bright in the infrared, glowing with the heat of its youth. Its atmosphere shows signs of water and carbon monoxide and other typical giant planet fingerprints. It is, by almost any reasonable standard, an important, interesting object. What it isn't, at least not yet with full confidence, is clearly a planet. Historians, yes, again, planetary scientists, but it is fun to imagine them as sleepy historians of the galactic past, still argue whether GQ Lupi b formed as a giant planet would form, in a disk around GQ Lupi A, or whether it formed more like a binary companion, collapsing separately out of the same cloud that gave birth to the star. Different studies have pushed mass estimates up and down over the years. Some have clocked it in at 10 to 20 Jupiter masses, placing it near or across the deuterium fusion threshold. Others have argued for something at the lower end, until either its orbit is well measured, which takes many years at such a wide separation, or its spectrum is analysed more precisely. GQ Lupi b is likely to sit in that limbo zone. Here is the quirky tidbit. GQ Lupi b was one of the first clear direct imaging detections of a substellar companion around a young sun-like star. It helped pave the way for later direct imaging surveys that found objects like the HR 8799 system, Beta Pictoris b, and ROXs S42bb. It is, in some sense, a kind of founder's artifact in modern direct imaging. Without it, the field might have progressed more slowly. Light joke for tonight. GQ Lupi b is essentially the galaxy's most ambiguous job application. Is it a planet? Is it a brown dwarf? Yes. Next question. Astronomers have been filing follow-up observations for over 2 decades, and the answer remains: it depends. You can almost picture it in a committee meeting, leaning back in a dusty chair, arms crossed, refusing to pick a side. And honestly, why should it? The boundary itself is arbitrary. GQ Lupi b is simply being exactly what it is, while we humans argue about which label to paste on its forehead. The physical properties of GQ Lupi b are roughly these: a warm, bright infrared companion, temperature around 2500 Kelvin in some estimates, probably gaseous through and through, with turbulent young atmospheres that show spectral variability. Its radius is larger than mature Jupiter's, because young gas giants and brown dwarfs both have inflated, puffy atmospheres before they cool and contract. So, at a glance, GQ Lupi b might look as wide as some of our hot Jupiter champions. It is, however, very different in origin and setting. Instead of being boiled by its star, it is slowly cooling down at a great distance, emitting its heat into the cold surrounding space. For our quest tonight, GQ Lupi b is an excellent reminder of a crucial point. When someone says, largest planet ever discovered, you must ask, largest according to whom? By what measure? At what confidence level? If you define the largest as the most massive object that someone has called a planet, you could potentially include GQ Lupi b at its higher mass estimates, and it would certainly qualify. But then you could also probably include even more extreme objects that most astronomers would classify as brown dwarfs. If you insist on keeping to the planet side of the 13 Jupiter mass line, you have to adopt mass estimates that are often best guesses. This isn't bad science, it's just honest science. The universe did not build these objects to fit our definitions, and we are a young species with middling telescopes, still feeling the edges of what we can measure. A mainstream fact, direct imaging of young planetary companions, which GQ Lupi b exemplifies, has dramatically expanded our understanding of giant planets at wide separations. Many surveys now systematically hunt for these objects using adaptive optics, a technology that sharpens telescope images by correcting for the blurring of Earth's atmosphere in real time. Adaptive optics allows ground-based telescopes to achieve resolutions comparable to, and sometimes better than, space-based telescopes of a similar size. Without it, GQ Lupi b would almost certainly have been undetectable. The fringe tidbit is a beautifully speculative one. Some astronomers have wondered whether GQ Lupi b might itself host one or more moons, or perhaps a disk of its own, which would make it a kind of miniature planetary system within the larger system of GQ Lupi a. We cannot directly image such moons today, but if GQ Lupi b is a gas giant, it is a reasonable bet that it has at least a few substantial satellites. Somewhere, perhaps, there is a moon in that system, a little warm, rocky thing, orbiting GQ Lupi b under a dim reddish sky with a small, distant central star in the far background. The idea is lovely. Nobody has proven it, but nobody has ruled it out. If tonight you had to pick a mental image of GQ Lupi b, let it be this. A glowing, orange-red, oversized young gas world, whose age and mass are still being debated, drifting in the patient ring of space around a young star. Both of them freshly made in cosmic terms, still settling into themselves, still working out who they are. In that, GQ Lupi b is a little like the listener, still figuring things out and in no particular hurry. Remember it as you drift onward, because the next stop is a planet so new that it is literally still being born right in front of the telescope. HD 100546b. Now this is one of the most strange and wonderful candidates in the whole catalogue, because HD 100546b is not just a big planet. HD 100546b, if it really is a planet we may have caught in the very act of being born. And being born, in this case, does not mean a process that concluded 10 million years ago. It means a process still underway right now, in real time at the moment your telescope points at it. HD 100546 is a young, hot star about 320 light-years from Earth, in the constellation Musca. It is a Herbig AE/BE star, which is the category reserved for young, hot stars more massive than the Sun that are still surrounded by significant amounts of dust and gas. In HD 100546's case, the star is surrounded by a very impressive protoplanetary disk, a flattened, swirling halo of the leftover stuff that did not end up inside the star itself. This disk, seen edge-on, is exactly the kind of cradle in which planets are thought to form. In the late 2000s and early 2020s, astronomers using sophisticated direct imaging techniques picked up what appeared to be a bright, warm clump inside this disk, moving along with the disk's rotation, behaving in a way that suggested a real, physical object. They called it HD 100546b. If it is indeed a planet, HD 100546b is enormous, probably several times Jupiter's mass, and still embedded in the disk from which it is growing. That is astonishing. We are essentially watching a giant planet vacuum up gas and dust in real time. The planet, if it is one, is carving a gap in the disk as it sweeps up material. Dust streams flow into it. Hot gas piles up. The object glows in the infrared not only because it is young and warm, but because material is falling onto it and releasing energy. Historians still argue whether what we see at HD 100546 is a genuinely forming planet, a disk feature masquerading as one, or a brown dwarf in disguise. The case is strong but not ironclad, and the debate is an excellent one. The quirky tidbit is that HD 100546b may have a sibling, sometimes referred to as HD 100546c, which is closer to the star, also potentially still forming. If confirmed, this would make HD 100546 a system in which we are witnessing the birth of two giant planets simultaneously. This is catnip for planet formation theorists. Every piece of data from such a system is worth its weight in adaptive optics gold, because we simply do not have many laboratories where the formation process is so accessible. Light joke for the evening? HD 100546b is basically the galaxy's most dramatic cooking show. We've tuned in partway through, and we're watching an enormous souffle rise inside a very dusty oven, while a lively debate rages in the audience about whether this is actually a souffle or a very confused pancake. The oven itself is preheating, occasionally flinging hot air around, and the contestants, the planet, the disk, the star, and possibly a second baby planet, are all vigorously disagreeing about when things are done. Physically, HD 100546b is thought to be glowing at temperatures of roughly 900 to 1500 Kelvin, though estimates vary. It may still be growing, still accreting mass from the disk, though at a rate that is slowing down as the disk clears. Whether it will end up at 5, 10 or more Jupiter masses is unclear. It is entirely possible that in a few million years, when the disk has dispersed and the planet has cooled, it will sit in the catalogue as just another super Jupiter on a wide orbit, not terribly different from ROXs 42BB. But for now, it is a cosmic nursery scene, rare and precious. The mainstream fact is that direct imaging of a still-forming planet embedded in its birth disk is extraordinarily difficult, because the disk itself is bright and complicated. The telescopes involved, especially VLT/Sphere, Gemini/GPI, and later ALMA, have to subtract out complex disk features to isolate a single candidate object. Each new dataset can shift interpretations. HD 100546b is, in that sense, as much a lesson in the art of direct imaging as it is a discovery about a single planet. For our quest for the largest planet ever discovered, HD 100546b is a soft candidate. Its mass is high, plausibly around 5 to 10 Jupiter masses, but our uncertainty is wide. Its radius is currently inflated by its youth and by its ongoing accretion, but that inflation will shrink as it cools. If we ran the clock forward 1 billion years, HD 100546b might look like a perfectly ordinary large gas giant. What makes it remarkable tonight is the moment in its life we're catching it. Very few objects in the catalogue offer a glimpse of the birth process itself. This raises a broader sleepy point. The more we look, the more we realise that planetary formation is not an event but a process, and a messy one. Gas giants like Jupiter did not appear fully formed one morning. They were assembled over millions of years from disk material, accompanied by collisions, scattering, migration, sometimes violent rearrangements. HD 100546b reminds us that big and young are intimately related for many planets, and that what we see today is a snapshot of an ongoing story. The fringe tidbit is that some researchers have hypothesized that the complicated gravitational environment in HD 100546, a disk, possibly 2 planets, a massive young star, might produce exotic features like dust traps, large spiral arms, and even gaps within gaps. ALMA images of the system show intricate structures that may correspond to these features. Whether those structures are direct fingerprints of HD 100546b's formation or are due to other physics is still debated. Either way, the images look like cosmic artwork, beautifully geometric curves and rings of glowing dust, the kind of thing you might want as a quiet print on your wall, if your wall could handle staring at something that dents with story. Imagine, for a quiet moment, standing at a safe but impossible vantage point near HD 100546. A hot, bluish-white star takes up a reasonable slab of your sky, brighter than the sun. Around it, a flattened plane of faintly shimmering dust stretches out like a cosmic record on a turntable, with rings and gaps and a general sense of organized chaos. Somewhere in that plane, hidden and yet detectable, a glowing clump rotates, drawing material into itself, slowly becoming a planet. A younger sibling, maybe, does the same further in. And the whole composition from your vantage is silent, beautiful, and patient. This is what gas giant formation looks like when you catch it. This is what Jupiter itself might have looked like 5 billion years ago from a similar quiet vantage. Remember that connection. because it is the kind of thing that makes astronomy and this sleepy script feel a little bit personal. Next, we will meet a planet that doesn't need a host star to exist at all. Now we drift to 2M1207b, and 2M1207b is, depending on how you squint, either the first exoplanet ever directly imaged, or one of the strangest cases of mistaken identity in cosmic biology. It was discovered in 2004 by astronomers using the Very Large Telescope in Chile, only a year before HD 100546b became interesting, and it made headlines for being the first directly imaged planetary mass companion to another substellar object. Here's what you need to know. 2M1207a is a brown dwarf, one of those not-quite stars you remember from earlier in the night. It floats in the TW Hydrae Association, a group of young stars and substellar objects about 170 light-years from Earth. 2M1207a is roughly 25 Jupiter masses, comfortably into brown dwarf territory. Around it, at a distance of about 40 astronomical units, orbits 2M1207b, a planetary mass companion estimated at around 3 to 5 Jupiter masses. So here's a fair question. Is 2M1207b really a planet if its primary is itself a brown dwarf? Definitions again. Some astronomers argue that a planet, strictly speaking, orbits a star. If your primary is a brown dwarf, then technically your companion is not orbiting a true star, and therefore the word planet may not apply. Others argue that it does not matter. If the companion is below the 13 Jupiter deuterium fusion threshold, and if it orbits a bound system, it counts. Historians still argue whether 2M1207b is a planet, a planemo, or some other category with a hyphen in it. Here is the quirky tidbit. 2M1207b, being a young object, is still puffed up and warm with the heat of its formation. Its temperature is around 1200 to 1500 Kelvin. Its radius is significantly larger than Jupiter's, possibly around 1.5 times Jupiter's radius. And because it is easier to image against the comparatively dim background of a brown dwarf than against a bright star, astronomers have been able to learn quite a lot about its atmosphere. Spectra suggest a hot, cloudy atmosphere with dust, methane, and possibly exotic condensates. It is, in miniature, an independent gas world, warm and red and slowly cooling. Light joke for the middle of the night, 2M1207b is the galactic equivalent of a child orbiting a teenager at a family reunion. Neither of them is the adult in this family. Both are small, both are still growing up, and yet technically the teenager is taller and older, so the dynamic sort of works, except that from any distance it looks like two kids gently playing catch in the corner of the universe, while the grown-up stars are off doing grown-up things. The mainstream historical fact is this. 2M1207b, announced in 2004 with follow-up work in 2005 and beyond, became a textbook example of direct imaging at substellar masses. It proved the technique could find planetary mass companions, and it opened the floodgates for later direct imaging successes like the HR8799 system, Beta Pictoris b, and the super Jupiters around A-type stars. Every direct imaging survey since owes a little bit of its confidence to 2M1207b. You can almost feel the imagery. A faint reddish-brown dwarf hangs in space like a smouldering ember. A second, smaller, redder ember orbits it at a wide distance, slowly cooling from its own formation heat. The whole scene is lit not by any bright star, but by the two objects' own internal glow. They are practically a double lantern in the black, and neither lantern has enough fuel to become a proper sun. From a safely impossible vantage point, you might see the brown dwarf as a dim orange ball, maybe the size of Jupiter, hanging in the distance. the planet would be harder to make out, a small warm smudge 10% as bright, off to one side. Between them, empty dark. Around them, the faint pinpoints of distant stars in the TW Hydrae Association. The whole system feels cosy in a minor key way, the way a campfire feels cosy in a vast wood at night. Is 2M1207b the largest planet in the universe? No. Its 3 to 5 Jupiter masses puts it comfortably away from the brown dwarf frontier, but it's not close to the top of the mass rankings, nor does it have a particularly huge radius compared to the ultra-puffy hot Jupiters we've seen. What it is, however, is a quietly important champion for the very idea that we can see a planet directly across interstellar distances and learn something about it. For the purposes of tonight's quest, 2M1207b is a reminder that the category of planet itself is wobbling under its own weight. We find things at different masses, in different orbits, around different kinds of hosts. Some clearly qualify, some clearly do not. Some fall into the grey area and force us to rethink the categories. The fringe tidbit is that 2M1207b, because it orbits a brown dwarf and is itself planetary mass, has sometimes been proposed as a kind of test case for alternative formation scenarios. Did it form in a disk around 2M1207a, the way classical planets form? Or did it collapse separately out of a cloud at the same time as the brown dwarf, making them more like a miniature binary? The mass ratio between the two objects is relatively high, roughly 1 to 5 or 1 to 8, which is unusual for classical planet formation but perfectly normal for binary formation. Again, the answer may lie somewhere in the middle, with elements of both processes. It is worth noting that other directly imaged systems like the HR8799 system, with its 4 gas giants, the PDS-70 system with its forming planets, and the Beta Pictoris system with its imaged companion, all fit into this same broad conversation. Each was a leap forward in our ability to pick out faint dots of planetary light against the glare of a host. Each added evidence that big, wide, directly observable planets are a real and probably common feature of the galaxy. You let the thought settle. Somewhere tonight, in the direction of the TW Hydrae Association, a small warm ember continues its patient, long orbit around a larger ember, and both glow quietly in the empty woods of space, for no audience at all except the occasional astronomer who bothers to look. That sounds poetic, but it is also simply true, and 2M1207b is a gentle reminder that the idea of the largest planet is less important than the idea that there are planets out there at all, in every size, in every configuration, around every type of host, most of them simply minding their own business. Remember 2M1207b as one of the founding members of the Direct Image Planetary Club, a small, warm, argued-over world that helped prove we could see such worlds at all. Now, in the next section, we'll pull back and think about the bigger question. What do we even mean by largest? Radius? Mass? Some uneasy combination of both? You sink a little deeper into the pillow, because now comes a section that is less about a specific planet and more about the quiet, semantic argument at the heart of our whole quest. Largest is one of those English words that pretends to be simple. It slides into a sentence confidently, as if we all know what it means. But in astronomy, largest can mean several very different things, and which one you pick dramatically changes who wins the cosmic prize. Largest by what measure? Let us, with great sleepy patience, lay out the options. Measure number 1, largest by radius. This is the straightforward one. Take the planet. Measure how wide it is from one edge of its cloud tops to the other. Compare that width to other planets. In this competition, the winners are the bloated hot Jupiters. Planets like TRES-4b, WASP-17b, KELT-9b, HATP-67b, and WASP 103b have radii around 1.6 to 2 times Jupiter's. Some claim even larger. In this competition, size is literally width, and density is low. You get puffy, low-mass, overheated balloons floating near brilliant host stars. Measure number 2, largest by mass. This is the more impressive sounding one. Take the planet. Figure out how much matter is in it. This does not have to correspond to how wide it is. A planet can be 10 Jupiter masses, but only slightly larger in radius than Jupiter, because adding mass past a certain point makes the planet denser, not wider. In this competition, the winners are the super Jupiters on wide orbits, like some of the HR 8799 planets, ROXs 42BB, Beta Pictoris b, and many directly imaged companions. Their masses range from a few to more than 10 Jupiter masses. If you push the mass higher, above 13 Jupiter masses, you bump into the brown dwarf boundary, and the conversation gets philosophical. Measure number 3, largest by volume. This is just a consequence of largest by radius, because volume scales as the cube of radius. So the volume winners are also the puffy hot Jupiters, even more dramatically so, because the cubing magnifies any width advantage. Measure number 4, largest by density. This one is almost a joke. Some extreme Jupiters are so dense that a teaspoon of their cores would weigh more than a truck. But density is not what most people mean by largest. Measure number 5, largest by age. This is where things get cosmological. The oldest known gas giants may have formed around some of the first generations of stars. They are not bigger necessarily, but they are older. In a loose sense, an old giant planet is larger in the time dimension. And measure number 6, which astronomers secretly care about most, largest by significance. This is the championship that counts when we talk about the planet's role in advancing science. Jupiter itself is, in this sense, still the largest planet ever discovered for humans, because without Jupiter we would understand almost nothing about gas giants. The first exoplanet discovered around a normal star, 51 Pegasi b, is also in this significance hall of fame. Planets like HD 209458b, the first exoplanet to have its atmosphere detected, are significance giants. Significance giants are the ones that made us go, oh, so that's what the universe is like. Historians still argue whether public-facing largest planet headlines should specify their definition up front. Some journals gently insist they do. Some popular science articles just say largest, and let the reader untangle it. Either way, tonight you're well equipped to decode the headlines, because you now know the hidden asterisk. The mainstream historical fact worth remembering here is that, for a long time, when someone said, the largest planet ever discovered, they almost always meant the largest by radius, not by mass. That is because the transit method, the workhorse of the large surveys like Kepler, directly measures radius. Mass requires a separate measurement, usually by the wobble method. Radius was the first number in hand, and it became the go-to metric for rankings. But as direct imaging surveys have matured, the mass-based view of largest has grown more prominent, and both metrics are now considered in tandem. The quirky tidbit is that because of this, the largest planet ever discovered has changed hands many times over the past 20 years, like a title belt in a slow-motion wrestling match. Early winners like HD 209458b were relatively modest in both size and mass. Then came TRES 4b, then WASP 17b, then WASP 12b, then HATP 32b, then HATP 67b, then KELT 9b, and along the way various announcements suggested one or another as the new largest. Each title period lasted a few months to a few years. If you want to be picky, you can almost build a timeline. The light joke tonight is that asking what is the largest planet ever discovered is a little like asking what is the tallest building in the world. On any given day there's a clear answer, but the list is always being updated as people build bigger towers, and behind every tallest claim there are multiple definitions. Highest roof, highest occupied floor, highest architectural detail, and so on. Different skyscraper organizations use different criteria. Astronomy is the same, except nobody is using cranes, and the towers in question are, again, made of cotton candy and orbit backward. Physically, the distinction between radius and mass has another practical consequence. A planet's scientific interest often depends on which dimension is dramatic. If you care about atmospheric chemistry, you probably want a planet with a large radius, because a large radius gives a big transit signal and lots of atmosphere to probe. That is why HATP 67b and HD 209458b are so commonly studied. They are natural laboratories. On the other hand, if you care about planet formation, gravitational dynamics, or the boundary between planets and stars, you probably want a planet with a large mass, because mass is what governs gravity, orbital stability, and internal fusion. Direct image superjupiters are prized for exactly this reason. The fringe tidbit is that some researchers have argued for entirely different metrics altogether. For example, angular momentum, a measure of how much rotational energy is tied up in a planet's spin and orbit, might in some sense capture largeness better than either radius or mass. Others have argued that planets should be classified by their atmospheres, or their host star type, or their orbital eccentricity. These alternative taxonomies do not replace mass and radius, but they supplement them. The field is, in a quiet way, still figuring out which categories really matter. You settle back as the whole question softens in your mind. The universe does not rank its planets. Humans rank them, and rankings are tools, not truths. Somewhere out there, a whole population of giant planets, of all possible masses and radii, exists more or less indifferent to our lists. We pick what to measure, we measure it, we argue about it, and then we move on. Tonight, you are picking a quiet winner for yourself. The planet that feels the largest to your sleepy imagination. That might be HAT-P-67b with its cotton candy radius, or it might be a 10 Jupiter mass superjupiter hanging in the long dark, or it might be the very idea that somewhere, right now, a future record holder is simply orbiting, unnoticed, waiting for us to catch up. Remember this as we zoom into theory in the next section. Let us get dreamy and theoretical for a moment, because one of the most interesting questions in all of planetary science is also one of the simplest. How big can a planet possibly get? You might think the answer is unlimited. Stack enough mass, get a bigger planet. Stack more, get a bigger one still. But the universe, annoyingly, does not cooperate with this intuition. There is a soft ceiling on how big, specifically how wide, a gas giant can ever be, and that ceiling emerges from the physics of hydrogen and helium under gravity. Here is the rough picture. A gas giant planet is essentially a giant ball of hydrogen and helium held together by its own gravity. As you add mass to it, two things compete. First, there is more stuff, which naturally wants to make the planet bigger. Second, there is more gravity, which compresses the stuff into denser, more compact forms. For low masses, adding mass wins. Each additional gram of hydrogen adds more width, but as the planet grows heavier, gravity starts winning. Hydrogen, under enormous pressure, becomes increasingly degenerate, which is a fancy way of saying that its electrons get packed together so tightly that they resist further compression only reluctantly. Past a certain threshold, adding more mass actually makes the planet smaller, not larger. This transition happens roughly at around 1 Jupiter mass. Below that, more mass, more size. Above that, more mass roughly same size. From about 1 Jupiter mass up to about 13 Jupiter masses, gas giants cluster around similar radii, often between about 0.9 and 1.2 Jupiter radii, once they have had time to cool and contract. If you add even more mass, past 13 Jupiter masses and into brown dwarf territory, the object gets a little smaller again, and then, near 75 Jupiter masses, when hydrogen fusion begins and a proper star ignites, the object suddenly starts growing again, because now heat from fusion supports the star against gravity. The upshot, and this is a weird, beautiful fact, is that gas giants, brown dwarfs, and the smallest red dwarf stars are all approximately the same size. Jupiter, a 30 Jupiter mass brown dwarf, a 70 Jupiter mass cool red dwarf. All of them are roughly 1 Jupiter radius across. They differ in mass by almost a factor of 100, but they do not differ much in size. That's why, visually, a big Jupiter-like exoplanet, a brown dwarf, and a small red dwarf star, if you could see them side by side without context, would all look similar in scale. The difference is in their internal temperatures and fusion. Historians still argue about the exact radii one would expect at each mass, because the details depend on the planet's age, temperature, composition, and irradiation. But the broad picture, this plateau of sizes across a huge range of masses, is well supported. Here's the quirky tidbit. This plateau, this narrow band of Jupiter-like widths, is why the list of largest planets by radius is dominated by puffed-up worlds. To beat Jupiter's radius by a lot, you really need something extra. You need a planet that is being actively inflated, typically by close proximity to its star, strong internal heating, or unusual magnetic activity, to push its atmosphere outward against its gravity. This is why all the real radius record champions are hot Jupiters. Cold gas giants, like Jupiter itself, like Saturn, like the super Jupiters on wide orbits, just don't have the energy source to balloon up. They sit at the natural equilibrium of their mass. The light joke for tonight is that if you imagined a cosmic scale where the x-axis is mass and the y-axis is radius, most gas giants and brown dwarfs form a kind of plateau, like a long, flat mesa. There's a little dip at the boundary between planets and brown dwarfs. Then, at the stellar end, the plateau abruptly rises as fusion kicks in. Cartoonishly, it is a cosmic roller coaster that mostly stays flat and then suddenly goes up at the station. Anyone looking for the biggest planet ever is essentially running back and forth on the flat part, arguing about which specific inch of mesa is 0.5 millimeter taller than the other. Physically, the maximum radius a gas giant can reach depends on just how much extra heat you can pump into it. For irradiated hot Jupiters, simulations suggest radii can reach up to about 2.5 Jupiter radii before the planet becomes unstable to losing its outer layers. Beyond that, the atmosphere simply escapes faster than it can be replenished, and the planet cannot maintain its puffy size. So we should expect, even with better observations, that the largest by radius planets will sit at around 1.8 to 2.5 Jupiter radii. No matter how many more we discover, we're unlikely to find a planet 10 Jupiter radii across, because such a planet could not exist in a stable configuration. The physics does not allow it. The mainstream fact tied to all of this is that this size ceiling is a prediction of stellar and planetary structure theory, going back decades to the work of astronomers like Kumar and Hayashi in the mid-20th century. They worked out using equations describing self-gravitating balls of gas, the mass-radius relationship across the planet-brown dwarf star transition. Their predictions have held up remarkably well against modern observations. Every time someone finds a new bloated hot Jupiter, it lands somewhere on the predicted curve, with maybe a little scatter. The fringe tidbit is that some theorists have explored weirder possibilities. What if a planet were composed of something other than hydrogen and helium? Could a planet of a different composition be much larger? Generally no. Denser compositions, like those involving heavy ices or rocks, produce smaller planets for the same mass. Only hydrogen-dominated compositions produce gas giants, and those are stuck on the plateau. Occasionally speculative work has imagined more exotic compositions, such as primordial deuterium-rich material or unusual layering, but nothing really escapes the basic ceiling. Another fringe idea is that early universe planets, formed from primordial gas without heavy elements, might have slightly different structures, because they would lack the metallic oxide clouds and other features that help to hold in heat in modern gas giants. Whether such ancient planets exist, and whether they would be larger or smaller than today's giants, is still a matter of speculation. So far, we have not directly detected any primordial composition planets, but the search continues, especially with deep infrared observations of old systems. You rest with this picture. The universe tells us gently but firmly that it does not reward you with more size for piling up more matter. Instead, it shows you a strange, remarkable plateau where planets, failed stars and smaller stars are nearly all the same approximate width. Jupiter, from this perspective, is not a small version of a bigger class. Jupiter is essentially the template. It is the shape the universe seems to want to make whenever gas collects in sufficient quantity. The largest planet ever discovered is, in an important sense, never going to be more than about 2.5 times Jupiter in radius, no matter how many more we find. That is the ceiling. That is the quiet physics hiding behind our cosmic rankings. Remember the plateau, because in the next section we'll come back to one of the juiciest mysteries related to it. Why are so many hot Jupiters ballooned up beyond what simple models predict? The inflation mystery. This is one of those charming phrases that makes planetary science sound slightly theatrical, and honestly it deserves to. For decades, astronomers have known that a significant fraction of hot Jupiters are larger than they should be based on standard models. The planets are hotter, puffier, and lower in density than what pure mass and radiation balance would predict. Something is inflating them beyond expectations, and for a long time nobody was entirely sure what. You can feel the appeal of the problem from your pillow. There is a warm, puffy pastry inevitability to it. Here are these gigantic planets orbiting close to their stars, and they are, again and again, coming in a little bigger than the model says. The excess puff is not tiny. Some hot Jupiters are 20, 30, 50% larger than the baseline models would predict for their mass, age, and irradiation level. Across the whole population of hot Jupiters, the scatter in radius is too large to be random. So what is the culprit? Possibility 1. Tidal heating. When a planet orbits close to its star, strong gravitational tides can flex the planet's interior, generating heat. If the orbit is slightly eccentric, not perfectly circular, the planet is squeezed and unsqueezed each orbit, and that mechanical work turns into internal heat. This heating can inflate the atmosphere. Some hot Jupiters' observed sizes match this model reasonably well. But for many, the orbits are too circular, or the planet's mass is too low, and tidal heating seems inadequate. Possibility 2. Ohmic dissipation. This one sounds exotic, but is actually quite elegant. In a hot Jupiter's atmosphere, ionized particles flow with the high-speed winds. These flowing ions, interacting with the planet's magnetic field, induce electrical currents deep in the atmosphere. Like a toaster, those currents dissipate electrical energy as heat. Over millions of years, this ohmic heating can deposit significant thermal energy into the planet's interior, slowing its cooling and keeping the atmosphere inflated. This mechanism neatly explains why the most inflated planets tend to be in an intermediate temperature range, where winds are strongest but not too strong. Possibility 3. Delayed contraction. Young gas giants are naturally puffy because they're still hot from formation. Normally they contract as they age. But if for some reason a hot Jupiter's cooling is slowed by stellar irradiation, by internal heating, by opaque atmospheric clouds that trap heat, its contraction can be delayed and it ends up larger than it would otherwise be at its age. Possibility 4. Enhanced opacity. If a hot Jupiter's atmosphere contains unusual amounts of certain chemicals that absorb infrared radiation, it can hold in its own heat better, much like a thicker blanket. The interior stays warmer longer and the atmosphere stays puffier. Possibility 5. Atmospheric loss feedback. As discussed before, very puffy planets lose mass to space. As they lose lighter components preferentially, their atmospheres may get denser, or they may be heated by the very process of escaping gas. The effects on size are complex and sometimes cut against simple inflation, but in some regimes they may help. Historians, atmospheric modelers, still argue which of these mechanisms dominates, and it is almost certainly not a single cause. Different planets probably owe their puff to different combinations. Ohmic dissipation tends to be favoured as the leading explanation for many hot Jupiters, especially those in intermediate temperatures, but tidal heating, delayed contraction, and enhanced opacity all play supporting roles. The mainstream fact tonight is simple. The inflation problem has driven a huge amount of theoretical work in the past 2 decades. Every time a new puffy hot Jupiter is found, models are refined and tested against it. Over time, the predictions have improved, but the fact that hot Jupiters are on average larger than you'd naively expect remains one of the most interesting empirical signatures in exoplanet statistics. The quirky tidbit: some researchers have even considered whether magnetic fields in hot Jupiters might be vastly stronger than our classical models predict, potentially enough to affect atmospheric dynamics in ways we have yet to fully characterize. If true, it could change our understanding not just of inflation, but of how these atmospheres evolve over time. The light joke tonight is that if a hot Jupiter were a person, it would be one of those people who insists they absolutely did not have that extra slice of cake, and yet, here we are, in fabric that is noticeably tighter than last week. The excess is real, the cake is implicit. The explanation is a complicated committee of contributing factors, each of which, on its own, feels barely enough to justify the change. Physically, the inflation mechanism matters not just for radius rankings, but for atmospheric properties. Puffier planets have lower surface gravities, which means their atmospheres are more extended, which means transmission spectroscopy, shining starlight through the atmosphere during a transit, picks up more features. Puffy planets are in a sense better lab rats for atmospheric chemistry. Each large radius hot Jupiter is a natural experiment in how planetary interiors respond to intense stellar heating over long timescales. The fringe tidbit is that some researchers have explored whether planets could, in principle, be so inflated that they essentially become extended envelopes of gas with indistinct outer boundaries. These would be extreme cases, perhaps linked to rare stellar evolution scenarios. We have not found such an object clearly, but the idea that a planet's surface might be fuzzy rather than sharp is interesting to think about while drifting off. What if, instead of a clean cloud top, a planet had a slowly thinning haze that faded gradually into interplanetary space? In practice, many gas giants do have fuzzy boundaries, but extreme cases might be fuzzier still. For the quest for the largest planet ever discovered, inflation is absolutely essential. Without inflation, the radius rankings would be much tighter, clustered around Jupiter's radius with a modest upward spread. With inflation, we get the outsized champions TRES-4b, WASP-17b, KELT-9b, HATP-67b. These planets are only record holders because the universe happens to include physics that puffs up certain hot Jupiters beyond their natural baseline. If every planet were purely baseline, Jupiter itself would be the champion, and we'd have a much simpler and much less fun nightly script. You rest, warm in your own not-hot Jupiter bed, and consider the gentle irony. The planets in our story are oversized because of physics we do not yet fully understand. Their record holder status is a monument to our lingering ignorance. Every time a theorist closes one more gap in the inflation problem, the rankings might wobble. Every time an observer finds a new candidate with precise mass and radius measurements, the models have to explain it. It is ongoing. It is unfinished. It is exactly the kind of story the night is good for. Remember the inflation mystery, because it explains why the largest planet by radius title shuffles so often. And remember that, in the quiet physics of hot Jupiter interiors, some tiny current is buzzing gently in the dim, deep atmosphere of a faraway world, keeping its cloud tops inflated for no one's benefit. Next up, we'll dive inside one of these monsters and trace a careful path through its layers, from the outermost haze down to whatever strange heart it might hide. Tonight, let's take a gentle, entirely imaginary plunge into the interior of one of these giant planets. We're going to pretend, for the purposes of sleepy exploration, that we can drift through a planet like HATP-67b or TRES-4b without being crushed, melted, or otherwise embarrassed by physics. Strap in the imaginary spaceship, or rather unstrap, because we're going to float gently downward. The outermost layer is a thin, hot, tenuous haze, mostly hydrogen and helium, with traces of water vapour, carbon monoxide, methane, on cooler planets, and, if the James Webb Space Telescope is to be believed, possibly tiny quartz nanocrystals, those sparkling glass dust clouds we discussed earlier. The temperature here is still very high, perhaps 1,000 Kelvin, because stellar radiation pours in from the nearby star. Winds scream through this layer at thousands of kilometers per hour. If you could drift through it in your imaginary ship, you would feel, well, you wouldn't feel anything because you are imaginary, but the ship would be battered by supersonic gusts. Drift downward. The pressure rises. The temperature either rises or falls depending on the planet's specific structure and the radiation profile. By about 1 bar, which is roughly Earth's sea level pressure, you're in what we might call the cloud deck, the layer where most of the planet's spectrum-forming action happens. Here the chemistry depends heavily on temperature. In a hot Jupiter, clouds might be silicates, little droplets of molten rock. On cooler gas giants, clouds might be water, ammonia, or even sulfur compounds. In Jupiter itself, the clouds are layered, ammonia ice above ammonium hydrosulfide above water. In a hot giant, nothing so tame, just glass and metal fog, deeper still. By about 10 bars, you're well below the cloud tops. Pressure mounts. Temperature rises slowly. The gas is still mostly hydrogen and helium, but it is no longer fluffy. It is compressed, dense, almost like a warm supercritical fluid rather than a simple gas. At 100 bars, you're in what scientists call the envelope, the main bulk of the planet. The gas has become so dense that it is essentially an ocean, though an ocean unlike anything on Earth. It's an ocean of supercritical hydrogen and helium, warm and crushing, extending for thousands and thousands of kilometers, keeps sinking. At about 1 million bars of pressure, something strange starts happening to hydrogen. The molecules themselves break apart, and the electrons begin to drift freely, and hydrogen transitions into a metallic phase. Yes, metallic hydrogen. It is an electrical conductor. It flows. It is, for all intents and purposes, a liquid metal. And in the deeper parts of gas giants like Jupiter, Saturn, and most hot Jupiters, this metallic hydrogen ocean dominates the interior by volume. This is why gas giants have strong magnetic fields. The metallic hydrogen, swirling in vast currents as the planet rotates, acts like a dynamo, generating magnetism. Jupiter's magnetic field is the strongest in the solar system after the Sun's. Hot Jupiters and super Jupiters likely have even stronger fields, though measuring them is an ongoing challenge. As you keep sinking, if you could still somehow cope, things get stranger. Pressures of millions of bars and temperatures of tens of thousands of Kelvin. In this regime, any residual heavy elements, oxygen, silicon, carbon, begin to dissolve into the metallic hydrogen ocean. The classical distinction between core and envelope becomes fuzzy. Instead of a sharp, rocky core and a gas envelope, many gas giants may have a dilute core, where heavy elements are partially mixed into the surrounding hydrogen over a wide region. Jupiter itself may have such a dilute core, based on recent Juno spacecraft gravity measurements. And the quirky tidbit, inside the deepest interiors of some gas giants, carbon and helium may separate out in strange ways. Carbon, under extreme pressure and temperature, may compress into diamond. Tiny droplets of diamond may precipitate and slowly sink through the hydrogen ocean. Diamond rain. Yes, it sounds like an Arctic Monkeys B-side, but it is a real theoretical prediction. Helium may also separate out from hydrogen in a process called helium rain, where helium droplets precipitate and fall through the planet's layers. Saturn has been suspected of hosting helium rain for decades, and it might be responsible for some of Saturn's mysterious internal heat excess. Historians, or rather theorists, still argue about the exact structure of these dilute cores and about how universal diamond rain really is. Models vary. Observations, especially from gravity measurements by spacecraft like Juno, are slowly pinning down the details, but for most exoplanets we have only rough theoretical inferences, not direct probes. At the very centre of one of these giants, you finally hit either a small dense core of heavy elements, rock, ice, metal, or, if the dilute core model is correct, a region where heavy elements are simply more concentrated rather than forming a distinct ball. Temperatures here might be tens of thousands of Kelvin, pressures tens of millions of bars. Solid matter in any terrestrial sense does not exist. Instead, exotic quantum states of matter hold sway. And you, the imaginary drifter, would have been atomized dozens of times over by now. The light joke tonight is that visiting the interior of a gas giant is essentially the least hospitable vacation in the universe. Imagine a travel brochure. Start your journey in hurricane-force supersonic winds and quartz sandstorms. Descend into an ocean of supercritical hydrogen that grows hotter and heavier with every step. Encounter beautiful cloud decks of melted rock and occasional iron droplets. Swim through metallic hydrogen while your skeleton is politely reminded that it was never really a match for several million bars. Watch, if you can hallucinate through the heat, diamond droplets drifting down around you. Finally, disintegrate atomically at the centre, rates negotiable. The mainstream fact is that our best understanding of gas giant interiors comes from a combination of first principles, physics, and detailed spacecraft gravity measurements at Jupiter and Saturn. The Juno mission, in particular, has measured Jupiter's gravity field with unprecedented precision, allowing models to infer the distribution of mass inside. Those measurements have led to surprises. The dilute core idea, for example, arose from Juno data. Similar direct measurements for exoplanets are beyond our reach for now. We infer their interiors from mass, radius, age, and by analogy to Jupiter and Saturn, but the theoretical framework is robust and widely accepted. The fringe tidbit is that deep in the interior of supermassive planets right at the brown dwarf boundary, pressures may be high enough for transient deuterium fusion, briefly near the edges of planetdom. That flicker of fusion, if real, would be the faintest cosmic flame possible, a near failure of stardom, a whisper of what would have been. Some astronomers have argued that the very distinction between large planet and small brown dwarf hinges on whether this flicker happens at all. Historians still argue whether it should count as a categorical change. You soften and settle. Imagine, if you like, a vast warm ocean of metallic hydrogen inside a distant planet, currents swirling slowly, diamond droplets drifting down like rain in the dark, a dilute core glowing with leftover formation heat. This is, right now, happening inside many worlds across the galaxy. It happens without any audience. Next, we'll remember that these enormous planets probably come with moons, rings, and entire miniature systems of their own. Moons, rings, shepherd satellites, hidden debris disks. The grand giant planets of our galaxy are, almost certainly, not lonely objects. They are very likely the centre of miniature systems, entourages of smaller companions that orbit them, scatter around them, and occasionally fall into them. And yet, here on Earth, with our current telescopes, we have not yet confirmed a single exomoon. Not one. Hundreds of candidates, some very suggestive but no undisputed detection. You drift on this. It is a quiet, almost embarrassing fact. We can detect planets thousands of light years away by the fractional dip in starlight. We can measure atmospheric compositions across interstellar distances, but we have yet to nail down, beyond doubt, a moon around another star. And yet we are nearly certain exomoons exist, in vast numbers, because moons are what happens whenever a planet forms. Look at our own neighbourhood. Jupiter has at least 95 confirmed moons. Saturn has over 140. Uranus and Neptune have dozens. The pattern is clear. Gas giants hoard satellites. They have big gravitational wells. They form with disks of their own, and they capture wayward objects. It would be bizarre statistically if the many super Jupiters, hot Jupiters, and cotton candy giants across the galaxy were all moonless. Probability says they are swimming in moons. Observation just hasn't caught up. Historians, or rather exoplanet observers, still argue about the best method to detect exomoons. Some propose looking for small additional dips in transit-like curves, where the moon passes in front of the host star either before or after the planet. Some propose looking for transit timing variations, where the moon's gravity slightly alters when the planet itself transits. Some propose direct imaging of thermal emission from very large Neptune-sized exomoons. Every approach is hard. Every candidate requires careful follow-up. The most famous candidate, Kepler 1625b1, was announced as a possible Neptune-sized moon around a Jupiter-sized planet, but later work has cast doubt on it. The search is ongoing. Here is the quirky tidbit. Some theorists suspect that very massive hot Jupiters, the puffy giants orbiting close to their stars, may have lost their moons long ago. The combination of strong stellar tides and chaotic gravitational dynamics during the planet's migration into its hot orbit could have stripped its satellites, flinging them into the star or out into interstellar space. So the biggest, most studied giants in our catalogue may be, for precisely that reason, nearly moonless, while the quieter, wider orbit giants might be surrounded by cosy little systems we simply cannot yet see. It is a charming irony. The light joke tonight: Imagining a hot Jupiter is essentially imagining an arrogant CEO who moved to a penthouse and, over the course of several billion years, slowly drove all his old friends away, leaving only a distant, weary star as his remaining companion. Meanwhile, a super Jupiter on a wide orbit is basically a quiet introvert with a large, cheerful, extended family of moons who rarely call but who are always there. Then there are rings. Saturn, of course, is the poster child for rings in our solar system. Jupiter, Uranus, and Neptune also have ring systems, though much thinner. The question is whether exoplanets have rings too. Theoretical expectations say yes. Rings form whenever moons break up due to tidal forces, or when dust accumulates in stable orbital zones around a planet. There is one particularly famous ring candidate, J1407b, sometimes nicknamed Super Saturn. Observations of the star J1407 showed an elaborate multi-stage dip in brightness over several weeks, which was interpreted as a giant companion planet or brown dwarf, occulting the star with a massive ring system far larger than Saturn's, potentially hundreds of times bigger, with clear gaps suggesting moonlets. If confirmed in future observations, J1407b's ring system would be one of the most extraordinary structures ever detected, a planetary-scale analogue of a small protoplanetary disk. The original interpretation is debated, and follow-up studies have revised the picture, but the original eclipse signal is quite striking and has sparked a long discussion. Historians still argue about the exact nature of the object. Rings, however, tend to be short-lived on cosmic timescales. Saturn's rings, for instance, are probably less than a few 100 million years old and will likely disappear in a similar timescale. That means ring systems are relatively rare snapshots in any planet's long life. If you want to see a planet with spectacular rings, you probably need to catch it at the right moment. That may be why extreme ring systems like J1407b's are not everywhere. The mainstream fact is that neither exomoons nor exorings are currently confirmed in the catalogue, but they are expected to become detectable in the coming decade. The James Webb Space Telescope has already improved our ability to search for them. Upcoming missions like Plato, Ariel, and especially Roman, as well as ground-based extremely large telescopes, should push the detection threshold much lower. In 10 or 20 years, our picture of giant planets may include confirmed moons and rings as standard features. The fringe tidbit is that certain very large cold gas giants might host moons large enough to be considered planets in their own right, if they were on their own. Some theoretical works have explored the possibility of Mars-sized or even Earth-sized moons around superjupiters. Such moons, if they orbit in the habitable zones of cool stars, could be potential homes for life. Science fiction has imagined this scenario for decades, in books and films where the heroic astronauts explore a forest moon around a giant alien gas giant. The science behind it is real enough that some researchers seriously consider exomoons as candidates in the search for habitable environments. For our quest for the largest planet ever discovered, moons and rings are a reminder that the biggest planets are not isolated oddities, but probably the hearts of miniature systems. A super Jupiter like HR 8799b, a hot Jupiter like HATP 67b, a wide giant like ROXs 42bb. All of them are probably accompanied by smaller bodies, though we cannot yet see them. When we finally detect the first exomoon around one of these giants, it will feel like discovering that the planet we had been admiring was actually wearing a small, surprising lapel pin the whole time. The light joke tonight is that planets, especially the big ones, are essentially the galaxy's most possessive collectors. They scoop up debris, they attract small icy bodies, they co-opt wandering objects into their orbits, and they rarely let anything go. In the cosmic economy, gas giants are old money aristocrats with disorganized attics full of stuff they never throw away. You drift with that image. Somewhere out there, a massive puffy hot Jupiter is being circled, right now, by a ring of icy dust that nobody on Earth has ever seen. A super Jupiter at 100 astronomical units is orbited by a small moon too dim for our instruments, a moon that has never known a name, a moon whose surface, if any, is black ice under a faint orange sky. All these private collections of small objects circle quietly, indifferent, for their own reasons. The galaxy is crowded but private. Now that you've pictured the entourages, let's take the next step. What would it be like, imaginarily, to actually visit one of these giants? Not to be crushed, not to be fried, but simply to look. That's next. Alright, pack an imaginary bag. We're going to take a dreamlike, impossible, strictly not physically survivable flyby of one of the largest planets ever discovered. We will not worry about spacecraft engineering, radiation shielding, or fuel budgets. We will simply drift there, in your mind, at whatever speed feels polite, and see what it is like to approach a world that makes Jupiter look compact. Let's pick a giant somewhere near the top of the rankings. Imagine a world like HATP 67b, a wide, puffy, hot Jupiter orbiting a brightening subgiant. Our imaginary spaceship, equipped with unreasonably generous physics, ignoring technology, slides in from the outer reaches of the system. We approach from the night side first, because that makes for a prettier view. From 1,000,000 kilometers out, the planet is a vast rust-colored disk, its night side softly glowing in the infrared with its own internal heat. You can see dim cloud bands, fainter than Jupiter's, because hot Jupiters have winds that smear their atmospheres into relatively uniform patterns. A thin, fuzzy outer haze extends thousands of kilometers beyond what you'd call the surface, because the atmosphere is so puffy. There is no sharp edge, just a gradual thinning of gas until it fades into the background star field. Rotate slowly around to the day side. Now the planet blazes. Its side facing the star is at temperatures of nearly 2000 Kelvin, glowing orange-red even in visible light, with hot spots where atmospheric currents stall and heat concentrates. The host star dominates part of the sky. It is a blue-white subgiant significantly brighter than the sun, and its glare lights up the planet's cloud tops with a fierce, uninterrupted fire. No clouds drift across gently. Instead, streaks and turbulent cells churn the atmosphere at supersonic speeds. You see enormous wave patterns rolling across the day-night terminator, where hot and cool air mix in impossible ways. The light joke here is that if you tried to open the ship's window, you would not so much be blown out as gently vaporized, politely, like a breath on a winter morning, except the breath is the entire ship. The atmosphere of a hot Jupiter is not a place to go for a short stroll. There is no surface beneath you. There is no solid ground. There is just a gentle, relentless downward gradient of ever denser gas, hotter and heavier for tens of thousands of kilometers. Let's try imagining a cooler giant instead. Move to a super Jupiter like ROXs 42BB. Same imaginary ship. Different scene entirely. Now your view is dramatically quieter. The planet, at roughly 150 astronomical units from its cool young star, is nearly alone in a vast dark. The star itself is a dim reddish pinprick, smaller in your sky than the moon is from Earth. Your imaginary ship hangs near a massive deep red gas giant, its atmosphere glowing softly in the infrared, its own internal heat of youth giving it a beautifully warm palette. You see faint cloud bands, probably silicate clouds with a dusty reddish tint, drifting in a more leisurely way than on a hot Jupiter. Storm systems might rotate slowly, reminiscent of Jupiter's Great Red Spot but possibly larger. The planet's overall colour is a sullen cherry orange, gradually deepening toward the poles. The gravitational pull of this planet would be enormous. If magically you could stand on a small surface a certain depth in, you would be pressed into the ground by gravity many times stronger than Earth's. Your bones, for the fraction of a second before being disassembled, would find it a dramatic experience. A few smaller companions orbit this imaginary giant. Some planets in miniature perhaps, exomoons if we allow them. One of them is close enough that its thin atmosphere glows faintly in your view. Another drifts in a more distant orbit, a pale icy world with a cold frozen crust. Between them, rings of dusty debris form soft, ghostly arcs around the planet's equator. These rings are not as bright as Saturn's because the planet's formation left behind less reflective material, but they have their own quiet beauty. Historians, or exoplanet visualization artists, still argue whether this is what such a giant actually looks like, because we have never resolved the surface of a super Jupiter. All we have are infrared dots. But the imagination can fill in reasonable details based on what we know about Jupiter's structure and the likely conditions in a young, warm giant. The quirky tidbit is that a hot Jupiter's day-night temperature contrast can produce a bizarre feature, a permanent hot spot that sits slightly east of the substellar point, pushed by supersonic winds. If you watch such a planet rotate, you would see the hot spot stay put, roughly, while the rest of the atmosphere moves underneath. It is like there is a weather system that refuses to travel. On Earth, this would be like having a thunderstorm permanently positioned 30 kilometers east of a city, while the city itself keeps sliding slowly beneath it. The effect has been mapped by eclipse observations of many hot Jupiters, and it is one of the coolest confirmed exoplanetary features we have. Another quirky tidbit: because some super Jupiters are still young and luminous, they emit enough light that, hypothetically, moons around them might be bathed in their glow, even if the host star is far away. A moon orbiting ROXs 42Bb, for instance, might receive more light from the planet itself than from the distant primary star, turning the sky of that moon into an ever-present warm amber glow. Again, speculative, but entirely plausible. Physically, a real spacecraft designed to visit such systems would face enormous challenges. Travel times would measure in centuries at best, probably millennia, using current propulsion. Nuclear-powered cruisers, fusion drives, even far future concepts like laser sail propulsion would at best cut the time to a few hundred years for the nearest candidates. For most of the planets we have talked about tonight, round-trip missions are essentially out of the question for the foreseeable future. We will have to content ourselves with observing them remotely, carefully, from here. The light joke for the second half of the night is that imagining a visit to HATP 67b is basically the travel equivalent of imagining a weekend getaway on the surface of the sun. You can picture it. You can describe the scenery. You can map your route. You will definitely not be coming back. And yet imagining these visits is useful. Every mental flyby sharpens our sense of what these worlds really are. They are not abstract dots in databases. They are real places with real weather, real gravitational fields, real internal oceans of metallic hydrogen, real glowing clouds of quartz, real auroras flickering above their polar regions. Most of them are uninhabited, some are inhospitable, a few may be surrounded by moons that could themselves support exotic forms of life under heavily shielded conditions. The universe is enormous and strange and intricate, and the biggest planets ever discovered are, in their own way, monuments to the richness of what can happen when enough gas, enough time and enough physics come together. Remember this, a vast, slowly rotating gas giant somewhere out there in the dark, a faint ring perhaps, glinting in the infrared, a distant star that knows nothing of your attention. Carry that image into the last section, where we'll consider the hunt still to come and ease you gently towards sleep. You're getting sleepy now, and that's good, because this last section is where we wind the whole story down. We have travelled through definitions, through brown dwarfs and hot Jupiters, through puffy champions and directly imaged giants, through the strange science of inflation and the quiet promise of exomoons. We've imagined visiting planets that would kill us at any approach. We've met worlds that don't know they're in our catalogues and couldn't care less if they did. Now, as the night gets deeper, we look forward, briefly, at what comes next in the hunt, and then we ease the whole script into a soft close. The next decade promises a real golden age for largest planet rankings. The James Webb Space Telescope, already delivering astonishing observations of giant planet atmospheres, will continue to probe the compositions of the most puffed up and most mysterious worlds. Plato, the European mission launching later this decade, will search hundreds of thousands of stars for transiting planets and refine mass and radius measurements with unprecedented precision. The Nancy Grace Roman Space Telescope, due to begin operations in the late 2020s, will use micro-lensing to survey the galaxy for planets at wide orbits, including free floaters and super Jupiters that are hard to find any other way. The extremely large telescope in Chile, the Giant Magellan Telescope and the 30-meter telescope will, once they are operational, push direct imaging to new depths, potentially revealing giant planets in their birth disks around dozens of young stars. Somewhere in that coming flood of data is, almost certainly, the next largest planet ever discovered. It may exist right now. It may already have been observed, hidden in a dataset waiting for someone to notice it. Historians, all the ones we've called on tonight, still argue whether the ultimate record holder will be a hot Jupiter of extreme inflation, a super Jupiter at the edge of brown dwarf territory, or something stranger that we haven't named yet. Maybe a rare primordial giant from the early universe. Maybe a rogue planet wandering alone through interstellar space. Maybe a young world still coalescing out of dust. The answer will keep shifting, because largest is less a title than a question we ask over and over as the galaxy gradually reveals itself. Now let's let the pace slow. Close your eyes, if they are not already closed. You do not need to remember a single fact from tonight. You do not need to know whether TRES-4b has a lower density than HATP-67b. You do not need to keep track of GQ Lupi b's mass estimates or ROXs, 42bb's orbital radius. Those planets will keep being themselves whether you remember them or not. They have been there for millions, for billions of years. They will be there tomorrow when you wake. They will still be there in 1,000 years, long after you and I and everyone we have ever known have become simple warm memories in a vast patient cosmos. Think softly of a single quiet image, a gas giant somewhere in the dark, wider than Jupiter, perhaps drifting at the edge of a protoplanetary disk, perhaps scorched by a nearby star, perhaps cold and alone under a distant sun. Its clouds move slowly on its own schedule, with winds and storms and auroras it will never share with you. Its moons, if it has them, orbit silently. Its rings, if any, glint in starlight, and the whole scene floats inside a galaxy that contains hundreds of billions of similar stories, most of them unrecorded, most of them unnamed, most of them simply happening, quietly, in the dark. You're small and safe and warm, and somewhere in the same universe that contains that giant planet. Your breath settles, your heartbeat slows. The room around you is steady. The fan is humming. The blanket is heavy in the right way. The whole long journey we took tonight, from 1992 pulsar planets, through hot Jupiters and cotton candy giants, through forming worlds and direct-imaged companions, to the quiet question of what largest even means, is all already floating away into the background, into the kind, soft place where nightly stories go. Somewhere, on a giant planet we have not yet discovered, the sun is rising over a banded cloud. Somewhere else, on a giant we know well, a quartz cloud is drifting gently through a hot, thin sky. Somewhere else still, a small moon orbits a warm super-Jupiter in near silence. You will never visit any of them. That's okay. They are yours to imagine, and the imagining is what makes them close. Rest now. Let the numbers drift away. Let the names fade. Let your body soften into the mattress, and let the night hold you the way space holds those distant giants. Patiently, without judgment, without expectation. Tomorrow there will be new discoveries. Tonight there is only you and me and a quiet voice slowly ending. Sleep well, the universe can keep turning, you don't have to help.